Good evening to one and all. Today is day 4 at FDP. So today we have two sections. Section 1, Dr. Hai Sridhar, Professor and Bilani Hyderabad. He will take care. And Section 2, Professor D. Jaikrishnan, NIT Warangal. So sir will take that section 2. Now I request JD sir will give the brief introduction about Hai Sridhar sir. JD sir, you can proceed sir.
Thank you, sir. Thanks for giving me this opportunity. I welcome all the attendees. It's my privilege to introduce Professor I. Sridhar, sir. Professor I. Sridhar, sir, has done BTech in Chemical Engineering from NIT Warangal in 1993, MTech from IIT Delhi 1994, and PhD from BITS Pilani 2008. He has more than 25 years of experience in industry, academics, and research. He has published over 100 articles in highly reputed international journals, 4 book chapters, 1 patent, 60 conference proceedings. He has received sponsored projects worth more than 2.5 crores from various agencies like DST, CSIR, GAL, GAIL, HBL, etc. He has been actively involved in academic administration of BITS Pilani as Practice School Coordinator, Hyderabad Center, Associate Dean of Practice School and Students Welfare Divisions, besides heading the Chemical Engineering Department for 3 terms. He is currently Associate Dean, International Programs and Collaborations Divisions at BITS Pilani, Hyderabad campus. He has been elected as a Fellow of Telangana Academy of Sciences, FTAS, Fellow of Royal Society of Chemistry, FRSC, Senior Individual Member, INAE, Fellow Institute of Engineers, India, FIE, and a life member of IICHE. He has been featured in top 2% of world top scientists as per the data curated by Stanford University since 2020. He is on the editorial board of various international journals like Journal of CO2 Utilization, Scientific Reports, Environmental Science and Pollution Research, Biomass Conversion and Biorefinery, Discover Applied Sciences, Discover Chemical Engineering, etc. He has been an academic council member of various reputed universities like Osmania, JNTU Hyderabad, JNTU Kakinada, Anurag, MBGR Engineering College, Vijayanagaram, etc. He is the recipient of various awards like Dr. C.R. Mitra, Professor V.S. Rao Foundation Best Faculty Award for 2021 across all campuses of BITS Pilani, Directors Award for the Most Prolific Researcher 2024, and Abhinandan Award for his active role in setting up Hyderabad campus. 12 scholars have been done or pursuing PhD under his guidance. Besides many ME dissertations, BE theses, and projects, he has been working in the Department of Chemical Engineering, BITS Pilani, Hyderabad campus since its inception and has been associated with the institute for more than 2 decades now. His areas of research include CO2 capture and utilization, reaction engineering, and heterogeneous catalysis, fluid rheology, and wastewater treatment. So, thanks for giving me this opportunity. Over to you, Dr. Sridhar, sir. Thank you, sir.
Thank you. Thank you very much for your introduction. So, without wasting my time, just I'll try to move on to my presentation now. I share my slides now.
Yes sir, you can proceed sir.
Yeah, let me start my talk on the current topic of addressing global warming through carbon capture. First of all, I wish to thank Aditya University and Illumilai and their team and his team for inviting me to be on the panel of these speakers for this Atal AICTE sponsored FDP program. And I wish to congratulate for all the efforts being done in this particular program. And I am glad to note that lots of participants are registered in this program, which means that the topic that was selected by this particular team is fantastic and which is relevant as on today. So in that context, actually, I would like to talk on, because sustainability is one important, the keyword or buzzword going on now, and also low carbon economy, sustainability goals. So these things are the buzzwords now, of course, apart from the e-vehicles and all that. So for the last 10 years or so, I've been working in this area of carbon capture, which is one of the main tools to address the global warming. Apart from that, as mentioned by the colleague from Aditya University, I used to work in the wastewater. Of course, even now I'm working on wastewater treatment and the rheology and the chemical reaction engineering and so on. But this is the one area where I'm trying to focus more on, because it's more relevant today, because global warming is a very serious phenomenon that is, say, creating a havoc. I can use the word havoc in the entire world. And the unpredictable climate changes that we are seeing now, okay, unpredictable climate changes in the sense that If at all it has to be a summer, it has to be hot. Winter has to be cold, and but that's not happening now. No, when we get the rain, when we get the hot temperatures, we cannot predict, and when the floods will come, when that, so everything is unpredictable. The fundamental root cause for this entire thing is the global warming. So people across the world, there is something called Intercontinental Paris Agreement, where the world leaders meet and try to discuss how to address this global warming. And they have that, they have a goal of reducing the temperature rise of delta T by say 1.2, 1.5 degrees Celsius, because if the global temperature rise increases by say 2 degrees Celsius, it impacts the whole thing. It impacts the human life. It affects the entire ecosystem. It affects your disturbs the entire ecosystem. It not only affects our human thing, but also the other aquatic life and even the industrial thing. So global warming has to be controlled. That means the world leaders are now trying to bring in the temperature rise under control, say to say 1.2, 1.3 degrees Celsius. Otherwise, it is unbearable. Even the life cannot sustain. That's the reason why carbon capture becomes very important, because this is the tool which is a very successful tool to address the global warming. Because let me see, go through the slides now. If you look at what is the global warming, fundamentally, if I want to make you understand the nuances of the global warming, first of all, a gradual increase in the Earth's surface temperature, which is caused by the greenhouse gases in the atmosphere due to the anthropogenic or human activities, is what is called typically global warming. So fundamentally, it's a temperature rise, and that is caused because of the various greenhouse gases. Greenhouse gases consist of CO2, methane, NOx, and various other components like carbon monoxide and so on. Among all this, carbon dioxide is notorious. Carbon dioxide is a major contributor, major constituent of the greenhouse gases that leads to the global warming. Hence, if this carbon dioxide that is actually being released from various sectors is controlled, is captured or utilized or converted to something else, then I think the global warming naturally comes down. Hence, the carbon capture, which implies actually carbon dioxide capture. We are not actually capturing the carbon. We are trying to capture the carbon dioxide. We are trying to capture. Then the next level is the captured carbon dioxide can be converted to some useful chemicals like ethanol, methanol, amines, and so on. And that is what is called the CO2 utilization. CO2 that is captured getting converted to some useful chemicals, that is what is called the utilization. There is one more thing which is called the sequestration. So the CO2 can be stored somewhere. It can be stored within the sea. It can be stored in the microbes like algae and all that. That is called CO2 sequestration. So the entire technology is what is called CCUS, carbon capture, utilization, and storage. So this is a fundamental thing which now the people, the world across is focusing on, so that to keep the global warming under control. So trapping the sun's heat in the atmosphere like by gases like CO2, CO, and N2O, that's the reason why the global warming happens, because it all these molecules like CO2, CO, and NOx and all that, methane and all that, they capture the sunlight, and then that they'll try to keep inside them, and thereby they're making the planet warm, which is undesirable. These are the greenhouse gases. If I try to look at the reasons why the global warming typically happens, is because one thing is the fossil fuels. We are still dependent upon the fossil fuels in terms of the power generation, in terms of automobiles and all that, because we're using the petrol, diesel, everything. So, of course, slowly we are trying to move towards renewable energy sources like solar, wind, tidal, and all that, but still it takes a lot of time. We cannot replace the entire fossil fuels with the renewable sources in at least another few decades. It will take some time for the fossil fuels to be completely removed. So in our generation or next couple of generations, it is not possible. We need to stay with or live with it, live with the fossil fuels, which is due to the coal burning, the thermal. For example, now the power generation is mostly by the coal, and the coal is obtained is one of the fossil fuels. And so fossil fuel burning is one primary reason for the global warming, because all these gases contains the greenhouse gases. And the deforestation, naturally, if we are cutting down the trees, for we are making everything and constructing the buildings there, everything is becoming urbanization now. So we are cutting down the trees and then making it a concrete jungle. So what is happening is, if the plants are not there, plants are the carbon dioxide natural absorbers, because in the photosynthesis, as we all know, they take in the carbon dioxide, they release oxygen. So if we do not have the plants, naturally the amount of carbon dioxide that's actually captured by the plants as a natural absorber, they're not there. So deforestation is one more primary reason why there is an increase in the greenhouse gases like CO2 in the atmosphere, leading to the global warming. Even in the agriculture also, once we have the plant, once we complete the entire season, what we do is we burn the entire crop once we reap the whole thing. And that particular burning, all this, even the incineration, even the waste management, like solid waste management, where we try to again do the burning, that is called incineration. Even the agriculture also, we normally burn the entire thing before the entire crop gets ready for the next season. So all these reasons are leading to the global warming, because it happens to the greenhouse gases, the concentration of the greenhouse gases keep increasing in the atmosphere. If you look at the Delhi, I think the entire, if you look at any news agency now, any news now, the breaking news is the Delhi pollution. Delhi pollution, if you really look at, the main reason why the pollution is happening is because of this agricultural burning that happens from the Punjab, the nearby areas. And during the winter, the movement is very slow, because of which the concentration is very much there on the top. The movement is very less, so that the concentration gradients will not be there. It is always a constant, it's keep on increasing, because again, this effect is from the Punjab, the Haryana, that area. They burn the entire wheat fields, and the entire gases will now move to the Delhi part. That's the reason why the air quality index is coming down drastically. And it's really pity to note that the condition of Delhi, I think some people are comparing the scenario. A person staying in 1 hour in Delhi will, a 1 hour stay in Delhi, especially in some parts, is equivalent to smoking some 3-4 cigarettes a day, or 5 to 6 cigarettes a day, or 10 cigarettes a day. That means the number of hours that you stay in Delhi, they're actually equating that to number of cigarettes that you try to smoke. That is the impact. The lungs are getting spoiled, and it's leading to the pulmonary diseases and all that. So it's not a small problem. We are dealing with a very serious problem, and it's a global problem. Global warming is literally global problem, and the carbon capture. That's the reason why, because that is being the potential tool to address the global warming. People are now focusing on the carbon capture. So again, the consequences of the global warming can be rising temperatures, and that leads to drought. And if you try to look at the melting ice, if I try to look at the Himalayas and all that thing, because of the global warming, the ice cap reduces, and it melts, and the ice will convert to the water, and that will flood the region. It will lead to the frequent flooding, and it will change the ecosystem. For example, in the sea, the aquatic life, the microbes or the entire aquatic life that is there in this water, they can bear only up to certain temperature. If the temperature changes by even a single degree, or even a fraction of a degree Celsius, some of the aquatic life cannot even live. So we'll try to lose the ecosystem. For example, the fish, all that the ecosystem that is there within the water, they cannot sustain no drastic temperature changes. It requires a balance in temperature, and the global warming is causing the temperature of the water to rise, and because of which the aquatic life is getting disturbed, because of which the entire ecosystem is getting disturbed. And we try to see the extreme weather. If it is a summer, we are now looking at very high temperatures. In winter, it's a very, very low temperature. And because, as I told you, because of the melting ice and all that, the sea level will increase. The level of the sea, on an average, that will increase. It can cause wildfires. It can cause the poor air quality like Delhi, and wildfires, the health risks, and even the economic impact. Because the industrial activities also will come down because of the global warming. So it will have an indirect effect on the industrial outcome. The productivity also will get lost because sustainability is disturbed there. So current progress of the global CO2 emissions, if you try to look at the total energy, the reason again why the CO2 is increasing in the greenhouse gases is increasing in the atmosphere leading to the global warming is naturally the population of the world is increasing. Of course, the rate of increase of population may be different for different countries, but naturally overall the population is increasing. And mostly now the power requirement, energy requirement is increasing because each family is now having multiple. It's in Delhi. If you look at on an average in a family, there will be some 3 to 4 cars. Every person in the family will have a car. You imagine every car in a family, like 4 cars in a family, takes in some few liters of diesel or petrol. You can imagine what's the energy consumption, even the power, electricity that they consume. So because of interest, and people are cannot stay without AC now. So because of which the energy requirement has been increasing drastically, and because of which where the energy comes, power generation. And for to generate the power, we depend upon the thermal power and the coal, and that will lead to the carbon dioxide. So CO2 increase can be linked to the urbanization and the increase in the energy requirement, which is indirectly linked to the enhancement of the population and the lifestyle. And the global greenhouse gas emissions, if you look at, they exceeded 53.5 gigatons in the year of 2024. That's a huge value. Hope you know what's meant by gigaton. Mega, giga, tera. Mega is 10 power 6, giga is 10 power 9. Okay, that means 10 power 9 tons. You imagine that figure of 53.5 into 10 power 9 tons in the year 2024. And in that, carbon dioxide alone is a major contributor, which is nearly 37.4 gigatons. That means in the entire greenhouse gases, our carbon dioxide plays a prominent role, which is more than, I think, 60 to 70%. So that's the reason why the focus is more on the carbon dioxide, how to capture that so that the carbon dioxide is not released to the atmosphere. It is either captured and kept in a different form, or that is converted to some other useful chemical like CO2 methanation, CO2 utilization, and then it can be sequestered. So in August 2025, the latest thing, the carbon dioxide at Mauna Loa, it is one of the areas in US, the concentration of the CO2 in that area, this is near Florida in US, it is 425.8 ppm, which is very, very high. So that clearly shows, of course, it's only at one location. That clearly shows that even the other regions also, the amount of CO2, that is, the concentration of CO2 is rising to 300, 400 ppm, parts per million, which is really very high. So if you try to look at the annual CO2 emissions in terms of the world, in what way the various countries are contributing, I think in terms of the year-wise and the country-wise, in terms of billion tons on this, if you try to look at India is contributing not neither too high nor too low. It is there somewhere in between. In the year 2000 to last 2 decades, we are contributing to around, if you try to look at, around 15 to 16 billion tons, which is not a small value. And of course, when compared to China, China is a big contributor. If you look at the entire the red color, the maroon color, the entire thing is contributed by China because they're into manufacturing, they're into various other things there. So, and of course, the population is also very high, like ours. But still, in terms of the amount of the contribution, of course, we can be proud that India is not contributing to the global warming through the greenhouse gases to a very large amount. But other countries like China and so the international other countries like US and all that, they are contributing in a significant amount in spite of having a low population. But whichever country is actually contributing, ultimately the entire world is facing that havoc. So it's a global warming is a serious problem. So this is what is the solution now for the global warming, which is has to be addressed. As I mentioned, CCUS is the only tool. What is that? First of all, carbon dioxide has to be captured. Okay, that is one thing. That means we need to capture the CO2 so that it's not released to the atmosphere. The next thing is, and if I try to capture the CO2 alone, and the people naturally ask, okay, you are capturing CO2, what will happen to the captured CO2? What do you do with that? So naturally, the next question is, if at all suppose from the power plant, the flue gases are coming with CO2. Of course, we use some adsorbent technology or absorption technology. We try to capture the CO2, and the entire CO2 molecules are captured in the adsorbent. Then what we do with that adsorbent, which is having the CO2? So unless until you add value to the captured CO2, the technology cannot be implemented in the industry. The power sector will not come forward because they need to invest a lot to integrate their flue gas thing to the carbon capture technology, because that's a costly affair. So unless until they get value, that cannot be scaled up. It is not commercially viable. Hence, people are now moving towards the capture, apart from the capture, integrated with the utilization. That means the captured carbon dioxide, if that is converted to something useful, which is having a commercial value, like methane, like methanol, like amine, ethanol, which are again useful clean fuels, then that will work. That means the captured CO2 is being used to add value to some the economic value. Then the industries will come forward. So carbon capture, if that is integrated with the utilization, then the technology becomes viable, and the various sectors like power sector or fertilizer sector and all that, automobile sector, these industries will come forward to use the technology of the carbon capture. And of course, one more thing is sequestration. That means we'll try to store the CO2 in underground or offshore, and that's called storage, completely a storage, and that is called the sequestration. That's like a carbon dioxide sink. CO2 is actually stored there. That is one more technology. But mostly the people are working on the capture and utilization, and some people are working on the sequestration, where we try to permanently store the CO2 within the ocean or offshore, or in terms of so even the microbes like algae and all that. If I now try to focus on the carbon capture, where I'm trying to work on, actually the carbon capture methodologies as a whole, they can be classified as three types. One is called the pre-combustion carbon capture. The second one is called the post-combustion carbon capture. The third one is called the oxy-fuel combustion capture. As the name suggests, the pre-combustion carbon capture means the fuel. It can be a solid fuel, it can be a liquid fuel, it can be any fuel like coal and all that. It is subjected to high temperature and pressure, and then converted to a gas that is called syngas, and that is containing CO and H2. And if that is treated with steam like water, it can be converted to CO2 and then H2 and H2O also. And then these two gases, CO2, can be separated by using a different technology like adsorption or absorption. That is one thing. That means here there is no combustion here. It is only thing is the fuel is getting gasified by trying to treat with the high temperature and pressure. It is directly the fuel is getting converted to a gas, and again that gas, in that gaseous mixture, the CO2 can be separated using a different technology. That is what is called the pre-combustion carbon capture. What is a post-combustion carbon capture, which is more popular than the pre-combustion, is it is like burning has happened. For example, in the power sector, there is a fuel like coal, it is burnt. Once the fuel is burnt, we'll get the flue gas. Now, capturing the CO2 from that flue gas, which is coming out after combustion, that is what is called the post-combustion carbon capture. So here there is a combustion. In previously, there's no combustion. There's no burning of a fuel. It's only converted to a gas. It's a gasified by trying to subject the fuel to high temperature and pressure. And then the gaseous mixture can be separated by using a different technology like membranes or adsorption and absorption. But post-combustion means after burning a fuel, we get the flue gas. In that flue gas mixture, we are trying to remove the CO2 and capture that. That can be done by using a solvent like liquid solvent, and the technology is called absorption. Absorption means ABSOR. I don't know how many of you are from chemistry or chemical engineering, or hope you understand that there are two technologies called adsorption and absorption. Absorption means ABSORPTION, which is a gas liquid phenomenon, where a gaseous mixture is made to contact a liquid solvent, where a gas, because of the solubility, will come inside the liquid, and thereby, for example, CO2, I'll try to take that solvent where the solubility of CO2 in that solvent is very high. when compared to other components of the gas. Thereby, the CO2 will be combined with the solvent. Of course, that solvent has to be again regenerated. That is one absorption. And absorption means it's a gas solid phenomenon. Instead of using a liquid solvent, we'll try to use a solid adsorbent like activated carbon, like coal fly ash, like various zeolites and so on. And when I try to make the flue gas be in contact with the solid adsorbent, that carbon dioxide will try to touch upon this the solid surface. It gets adsorbed in a physisorption or a chemisorption, and then other molecules will not, because it's a selective adsorption. Only the CO2 molecules. I'll ensure that the affinity of that adsorbent to the adsorbate of CO2 is very high, so that only CO2 will be pulled towards that solid adsorbent. Thereby, we can get the separation. Of course, we can also use membranes. But membrane technology is a bit costly because there is something called a fouling problem. So membrane, the running cost is very high. So membrane fouling is a serious issue. And since chemical solvent, which is absorption, actually the technology is very much there, and it is scaled up also. People normally use lots of amines as liquid solvents. But the problem with that absorption is, as I told you, once that solvent is taking the carbon dioxide within that, trying to again regenerate the solvent is a costly, energy intensive, and also it is environmentally non-benign process. It can lead to a secondary pollution. So that's the reason why people are now focusing more on adsorption. That means the gas solid type of thing, because there are lots of varieties of adsorbents available, right from the low value feedstocks, starting from the say the even the biomass, which is the agricultural waste, even the coal fly ash where we studied, which is industrial waste available. So adsorbents are lots of varieties are there, and it's a very simple process. It does not require a very costly equipment. It's a simple process. It can be easily scaled up, and regeneration of the adsorbent is not that costly when compared to regenerating a liquid solvent. So it is more clean and simple process. That's the reason why people are more focusing on adsorption based carbon capture. And of course, the third one is oxy-fuel combustion. So here also, there is a combustion. Only thing is, as the name suggests, the combustion is being done using the pure oxygen, not air. Typically, combustion normally happens in the presence of air. Instead of air, we try to use the oxygen, only pure oxygen. That is called oxy-fuel combustion. That means using oxygen, we are trying to burn the fuel to get the flue gas, and then the CO2 and H2O that we get, if that is condensed, we get the CO2, which can be separated. That is called oxy-fuel combustion capture. This is also a good technique, but the problem is this is a costly affair, because to get the pure oxygen, because air is very cheap when compared to the pure oxygen, because we require at a larger scale air separators, where from the air we try to separate O2, N2 and all that, we can get oxygen. So this is a bit costly, but of course, again from CO2 and H2O we require condensation to get the pure CO2. Oxy-fuel combustion is still under the technology ready levels, is not at a pre-industrial or commercial level. It's still at the lab scale. Now, this is what is the picture-wise description of the various technologies. As I told you, the absorption, adsorption, membrane separation. There is, of course, the cryogenic distillation. There is something called chemical looping. So overall, if I try to sum up, these are the 5 different technologies that we have for carbon capture. As I told you, absorption, if the flue gas enters an absorber, where the solvent, the liquid, will try to take in the carbon dioxide, and apart from the carbon dioxide, the remaining gas will come out, and then the liquid solvent has to be regenerated. That is what is called stipper. So absorber and stipper is for regeneration. That means the carbon dioxide which has gone to the liquid solvent, now again I want to use the liquid solvent again and again. So which implies I need to remove the carbon dioxide now. So that is what is called stipping. That means I will try to remove the CO2, and that CO2 can be captured, which is coming out through the means of stipping. Similarly, adsorption. Only thing is, the difference between absorption and adsorption is, here that is a gas liquid phenomenon. Here it's a gas solid phenomenon. Here the flue gas is brought in contact not with the liquid but with the solid. That is called adsorbent. And this adsorbent will try to capture only the CO2, and the remaining part of the flue gas will come out. And thereby again this adsorbent, like the previously the solvent is there, here also adsorbent contains the CO2. And adsorbent I want to use multiple times. I need to regenerate. I need to again remove CO2. I can use simple calcination, the thermal way, thermal generation, where if I try to heat that adsorbent to a high temperature like 400 degrees Celsius for a couple of hours, I can that CO2 will come out. I can capture that, and again my fresh adsorbent is back. I can use it again. So this is adsorption, and the second one is called regeneration. Of course, even the stripper also can be treated as a regeneration. We are trying to regenerate the liquid solvent. Similarly, as I told you, membrane separation, though it's not commercially being utilized because membrane is a costly affair because of the simple reason of the fouling. So here the working principle is the flue gas again flows through a membrane. Hope you know what's a membrane. Of course, every one of us have the water filters in our homes. So what we use is there's a membrane, RO membrane, the reverse osmosis membrane. So these are the fine filters. So the flue gas will pass through the membrane, and that membrane will try to retain only the CO2 molecules, and every other molecule can come down, can pass through. Okay, only CO2. That means the pore size of a membrane can be designed in such a way that the membrane will not allow the CO2 molecules to pass through, and it will allow everything else to pass through. So that CO2 can be captured. So that is the one more membrane separation, but fouling has to be addressed there. Cryogenic distillation means, here as the name suggests, cryogenic means very, very low temperatures. And distillation is nothing but separation of various components by using the difference in the boiling points or relative volatilities. So the flue gas will enter that column, and that column is maintained at very, very low temperatures. I can say minus 30, minus 40 degrees Celsius type of thing. Then we try to get various gases at various levels depending upon the relative volatility. At CO2, it will come out at one fraction. CH4 will come at one more fraction. N2 and H2 will come out. That means they come out at different temperatures, and we collect at different fractionations. So, but the thing is, for this, it requires a very, very low temperature. And we know that getting or maintaining such a very low temperature is again a costly process. It requires the what do you call the refrigerants, very highly effective refrigerants. Even the nitrogen also may not be sufficient. It requires even a powerful refrigerant. So cryogenic distillation is still under research stage. Only thing is absorption and adsorption. These two are mostly widely studied. Absorption has been commercialized, but the problem with that absorption is the liquid solvent is the regenerating the liquid solvent is a costly affair, energy intensive process, and also it leads to the environmental pollution. But adsorption is relatively clean process, and because of the availability of lots of adsorbent materials, we have wide choices to be made, and it can be cost effective. It is a simple process, and it's a clean process when compared to the absorption. So people are now focusing more on adsorption. And chemical looping is something which is different. Chemical looping, again, chemical looping, as the name suggests, there are two reactors. Of course, there can be only one reactor. Typically, in a physical sense, the reactor can be only one. But in one cycle, it is called as a air reactor. In second cycle, it's called a fuel reactor. So, for example, in the first cycle, say where the fuel reactor, the fuel will be loaded in the reactor, and that is actually there is a metal oxides will be acting as oxygen carriers. So it's like a chemical looping combustion. For every combustion, we require something like oxygen. Okay, we try to send through the air, or we can send through even metal oxide like CaO, MgO, and all that. So metal oxides, along with the fuel, they are burnt in the fuel reactor. Because of that, the CO2 and all that will come out. And the problem is, because of this metal oxide giving oxygen for the for burning to happen, there will be a depletion of oxygen. So the metal oxide will be now forming as instead of MEXOY, which is the original metal oxide, because of oxygen that is being lost for combustion, what we get is MEXO Y minus 1. In the next cycle, what will happen is this particular metal oxides which are getting depleted, they are passed through air. Air is passed through that particular reactor again. That means the same reactor. In one cycle, it will follow that air, the metal oxide, and then the metal oxides will be there. The fuel is burnt, and then the second thing, we'll pass that reactor, pass air through the reactor so that metal oxides are regenerated back, because in air there are oxygen molecules. So oxygen molecules will again will be adding up to the metal oxide which are depleted. So MExOy minus 1 will be again reformed as MExOy in an air reactor. That means again we can go for a fuel reactor, again air reactor, fuel reactor, air reactor. That means like fuel reactor is something like a combustion, air reactor is like a regeneration, where we are trying to regenerate my metal oxide so that it can continue for a longer number of cycles. So though the physically the figure shows two reactors, of course, in the absorption, adsorption, and the chemical looping, though the physically I'm showing the two reactors, actually the phenomenon of the combustion and the regeneration can happen in the same reactor but in the alternate cycles. So that's called the chemical looping. Why it's called looping? Because everything is again looped, everything is a closed circle, because nothing is being brought from outside. Whatever the metal oxide that we are taken in the beginning, the same metal oxide is being regenerated and reused again and again. Hence the same fuel, same reactor. That's the reason why it's called chemical looping process. And as I told you, among all the technologies that we are seeing till now, through which the carbon dioxide can be captured, be it adsorption or absorption or cryogenic and various other things, as I told you, my focus actually, I've been working in the technology of adsorption. The reason is this operation is very, very simple, it is flexible, and it can be easily scalable. And the second reason is I have wide range of adsorbents, even from low cost feedstocks like biomass, coal fly ash, and so on. And when compared to other technology, this is eco-friendly. That means this is environmentally benign process, and also it is energy efficient, because regeneration will not take too much of energy, unlike absorption. So it is environmentally clean process, as also energy efficient process. And also the one more advantage is it can give high capture capacity. That means the amount of CO2 that can be captured, I can express in terms of millimole per gram or gram per gram. That means number of moles of carbon dioxide captured per gram of adsorbent. So that can be very high. And even the same adsorbent can be reused for multiple cycles. And in our own studies, we could use up to 50 cycles. 50 cycles where my material has been proved to be stable, up to 50 cycles with a very marginal loss in performance. So, and that means this can go on. We can go on up to 100 cycles also. So, if a material is stable, it has got longevity, which implies the technology is commercially that can be taken up. So, it's feasible to scale up and it can be commercialized. These are the advantages of adsorption. So, this is a simple snapshot of a comparative analysis of various carbon capture methods. Absorption, of course, for every technology, there are few merits, there are few demerits. Similarly, for absorption, capture efficiency may be very high, and it can be regenerated by simple heating or depressurization. But as I told you, the disadvantages are many. The environmental impact, because the regeneration is leading to the secondary pollution, and it requires significant energy to regenerate the absorbent. That's the reason why the absorption is not economically viable. Adsorption, of course, definitely there are advantages because it can be easily recycled or regenerated. Of course, it's a high efficiency in terms of capture. But again, here also, in terms of regeneration, we do require energy because we need to heat that adsorbent to a temperature of 400 degrees Celsius up to for some 3-4 hours. That's called calcination. So calcination definitely requires energy, but when compared to absorption, then the requirement is relatively low. And chemical looping combustion, definitely it avoids energy intensive air separation because it's not oxy-fuel. If at all it's oxy-fuel, I require only oxygen, which requires air separator. That means I need to send the air to a separator, and in that air separator, I'll get oxygen and nitrogen, everything else out, and only oxygen part will be used. But in a chemical looping combustion, I can directly use air, and air is economically, no, it is not a costly thing. It's very much available there. So, but still, chemical looping combustion is still in the developmental stage. It's not, of course, in certain areas it is being commercialized, but still people are working in a large scale operations. And membrane separation, the process is developed for a very few gases, Of course, it has got a good efficiency, but the thing is, as I told you, high operational cost. Maintenance cost is very high because membranes are vulnerable to fouling. And cryogenic distillation, it's still a mature, it's a to be developed technology. Of course, technology wise, well known. Okay, the distillation is well known, and even a cryogenic thing is well known. But the problem is, it is not viable because to generate very low temperatures is a very costly affair. So it is only viable if at all the high CO2 concentrations are there. For example, if I want to capture CO2 from ambient air, this cryogenic distillation is not viable because in ambient air, the amount of CO2 present is only maybe in terms of ppm. But if I try to look at flue gases coming from various sectors, the concentration of CO2 can range between 10% to 20% to 30%, so on. But in terms of ambient air, which is also called, people are now working on direct air capture or ambient carbon capture. So this particular cryogenic distillation is not viable where the CO2 concentration is low. So various types of adsorbents that are available in terms of metal organic frameworks are there, and activated carbons are there, polymers are there, metal oxides are there, aerogel. People are now actually aerogel. I need to spend some time because people are now, if at all somebody is doing research now, people are focusing more on aerogels now in environmental application, not only in carbon capture but also in wastewater treatment and all that, because the aerogels means they are highly light materials, like what you call the thermocol balls will be there. They are so light and they are having a very high surface area, high porosity. That means that can capture, since the material is having a high surface area and high porosity, it can take lots of CO2 molecules onto that. But the problem is again the thermal and mechanical stability. So aerogels are employed, but stability is a problem. People are working on aerogels, but the stability will not be as long as like 30 cycles, 50 cycles, and 100 cycles. That may not be possible because they crumble. They crumble. Okay, so apart from metal organic framework, there is a covalent organic frameworks, which are nothing but say porous organic polymers. These are also called porous organic polymers, and also zeolites. Zeolites are nothing but aluminosilicates. So these are various options that we have as far as the adsorbents are concerned. And these are some of the reported literature. People have used various adsorbents and the gas composition that they have used, and CO2 uptake in terms of millimole per gram, how much they got. So these are various things. I will not get into the names of this. These are various adsorbents. Okay, Mg, MOF, that means magnesium modified MOF, and that ND, NDPMN, and all that. These are nothing but NN dimethyl 1,3 propene diamine. So I will not get into the chemistry part because it may be boring for some of you. And some names like UIO, EDA. UIO means this, sometimes the names of materials are actually given depending upon the university or the center, research center, which developed that material. For example, UIO is actually developed by, it is called University of Oslo. It's a University of Oslo has developed that, and that is modified ethylene diamine. So similarly, UIO means University of Oslo. So lots of universities or some materials. For example, I know that IICT at Hyderabad has developed a catalyst. So the catalyst is given name of IICT catalyst. So depending, it's like the name can be something. So if at all we develop some new material, the name we can give, and that's how the names can be given. So actually, our studies, if I try to look at my own research in this particular area, I got a project from CSIR where by using the coal fly ash, which is widely available in our thing, because we have tons of coal fly ash available, and we can use that coal fly ash as adsorbent. The reason is it's rich in aluminosilicates. It's like a zeolite. Aluminosilicate, so alumina is there, silica is there, metal oxides are there. It's rich in all this. So it's abundantly available, and it is having a potential of giving value added products. And thereby it's a very common industrial waste. If you do not use that in a proper way, what will happen is, yes, somebody is having some question, Pratap. So coal fly ash, that's one area where we focused upon, and we got very good results. The CSI project has been a huge success, and we are going for a next level of project where we take it to the commercial level. So fundamentally in coal fly ash, we have done two things. One is we directly employ the coal fly ash as an adsorbent, and second way is we derived certain materials like zeolites and all that from coal fly ash. Then we use those derivatives as adsorbents in the carbon capture, and both yielded very good result. For example, again in the coal fly ash, depending upon their composition, they can be of two types. Of course, CFA, coal fly ash, C type or F type. Only difference is the composition. In F type, the more of, apart from silica and alumina, the metal oxides also will be there in a significant amount. But in coal fly ash C, it is mostly silica and alumina, but with less of the CaO, MgO, the metal oxides. Fundamentally, it's only difference in composition. Depending upon which region of the coal that we have, the coal fly ash also can be of various grades. And we have taken both the grades also for our study. And this is a simple reactor that we used, which is a fixed bed reactor, where there's a heating process, the flow controls are there, the temperature control is there. Ultimately, we try to send the flue gas of required composition. At the end, we try to see through the gas analyzer what is the amount of carbon dioxide that is actually coming out. So if at all, it's a very simple one. Suppose I'm trying to send some 10 moles of carbon dioxide inside the reactor, where there's an adsorbent which is loaded. I'm getting 2 moles of carbon dioxide outside, which is analyzed by the gas analyzer. That means 10 minus 2, 8 moles of CO2 is getting captured. So if I want to calculate the percentage of CO2 capture, it's very simple thing. 10 moles of CO2 is sent, 2 moles is coming out. That means 10 minus 2, 8 moles of carbon dioxide is captured out of 10 moles. That means 8 by 10. It is 80% capture value. That's how the capture value can be easily calculated. It's a very simple one. And these are the results that we got. And if you look at, of course, we compared our result with the reported also. And if you look at the capture value, the last but one column, we got very, very high capture value, which is nearly 11.2 millimole per gram. So this is relatively very, very high. There's only one study which is reported slightly at a higher thing, which is a pure CaO. But pure CaO is a costly thing when compared to coal fly ash. We are using the coal fly ash. Thereby, if I try to make a combination of the cost versus performance, my adsorbent of coal fly ash derived adsorbent has given a very good performance, and we could publish in many this particular work in reputed journals. So fundamentally, if I try to look at what gave the best performance is, we try to we try to take the coal fly ash and mix it with some amount of CaO, the calcium oxide and magnesium oxide, a combination of calcium oxide, magnesium oxide, and coal fly ash. This combination has given a fantastic capture value, which is nearly 11 millimole per gram. And this is at a high temperature. This is a high temperature carbon capture. As you know, let me tell you, carbon capture can be low temperature, moderate temperature, and high temperature. So if at all, that means at the temperature at which the carbon dioxide is getting captured, that is how we can classify. So this comes under a high temperature capture value. There can be a moderate temperature, there can be a low temperature. Accordingly, we will try to take the materials also. Coal fly ash, since it can sustain high temperatures, we have taken the high temperature carbon capture. Suppose if I try to take material like MOF, this cannot sustain high temperatures like 500, 600 degrees Celsius. Thereby, I will not try to take a metal organic framework or covalent organic framework or polymers for high temperature carbon capture. I will try to use them for a moderate or to low temperature carbon capture. So depending upon the temperature of the capture that is required, I will try to select appropriate materials depending upon their thermal stability. So this is of course, we have done the experimental design. We used our the response surface methodology, and we got the capture values done. And these are the effect of various parameters like time, temperature, the flow rate, and adsorbent loading, how much of adsorbent, and the results clearly show. So using this, by studying the effect of these 4 critical parameters, the time, the temperature, the flow rate, and the adsorbent amount. So we could get the optimal values. We could get the optimal values, and at which we get the highest capture. So this particular thing we also have done. I think let me look at which is at 650 degrees Celsius with 20 gram sample, and I think that optimal conditions will be given at the end, which has given that 11 millimole per gram. But to reach that value, we have done a lot of homework, lot of optimization work, and to arrive this particular thing. And we did not do in a random manner. We optimized using a significant statistical experimental design. That is what is called response surface methodology, where we try to develop the experimental matrix. That means with minimum number of experiments, we can optimize the large number of parameters. If I do not use this experimental design, I'm trying to, I think all the people who are doing some research, you please make a note of this one. You may be working in different areas, but my advice to you is whenever you're trying to optimize or standardize any given process, try to use experimental design. And that can be done in various ways. And one of them is the response surface methodology, where we can, with the less number of experiments, we can optimize large number of parameters. If we do not use this, we need to use enormous number of experiments, which requires lots of time, lots of resources in terms of manpower, in terms of the material resources as well. That's a very cost affair. Even though it is not scientifically not valid now, people are not reporting in that crude way of optimizing. We need to do everything smartly. So the smart way of doing optimization is using the appropriate experimental design. And apart from that, we have done the stability studies also. Of course, for this material, we've done the stability up to say 12, up to 15 cycles. And the carbon capture value did not fall to a great value beyond, of course, from 11 millimole, it is coming down to 8 to 9. That is acceptable. So, and we also found that the amount of regeneration temperature, that means the regeneration, as we all know, it requires again heating. And the beauty is we found that by using that MgO, which is acting as an inert, that particular material is bringing down the regeneration temperature. That means the amount of heating that it requires to get my CO2 back, get my adsorbent back, that is getting reduced. That means that is leading to energy savings. So MgO is acting as a very good inert material, which is reducing the regeneration temperature, thereby because CO2 capture is a reversible process. So where in one cycle carbon dioxide is captured, in the reverse cycle carbon dioxide is again that can be removed. So the temperature at which this can be, the reverse reaction can happen, that can be reduced by using appropriate materials like MgO, magnesium oxide. So this is about, as I told you, the difference between CFE, coal fly ash, C type and F type and all that. And as I told you, the combination that gives the highest capture is CaO 50%, MgO 10%, coal fly ash 40%. And if you look at the composition of F type and C type, in F type thing, the CaO and MgO, that is a bit low, and C type, when compared to alumina, silica is there, and there is a significant amount of even the CaO, MgO, which is around 36% and 11%. So it's all about composition, and it's not in our hands. That is based upon the nature of coal that's available. So, and this is how we actually demonstrated that whether the material is stable in terms of its crystalline nature. So after fifth cycle, 10th cycle and 15th cycle, we have taken that adsorbent, we tested it for stability, and we found that the material is perfectly fine. In terms of the structural integrity, it is maintained perfectly well. So XRD studies clearly demonstrated that. So material is not losing its, say, the crystalline nature. So these are even the physicochemical attributes. We have done the SEM studies also, not only XRD, we have done the scanning electron microscope, the thing to understand about the morphology. Even the morphology also is not disturbed, even after 15 cycles. And of course, we have done as a nature of whenever we do some process optimization, we also do some kinetic studies to understand, to get a deeper insight into the process. What is the kinetic, how fast this particular carbon capture happens, what's the time required, what's the reaction order, and so what are the controlling parameters, is it reaction controlled or is it diffusion controlled? To understand all that, we try to fit in various kinetic models and try to understand that. We have done the kinetic studies, which is mostly of academic in nature. So we have done the kinetic parameters estimation by using that, say we estimated the Arrhenius equation parameters and we compared with the reported literature, and they're perfectly matching. And also we have done the thermodynamic studies to understand about the thermodynamic nature of the process. in terms of estimating the enthalpy change, entropy change, the Gibbs free energy change, and the constant of equilibrium. And then this is plotted there. And clearly, the negative sign of enthalpy is indicating that the process is exothermic in nature. And the same exothermic nature is the reason why the entropy is also negative. And the delta G being negative clearly shows that the process is spontaneous in nature. Okay, it's a spontaneous in nature, and we are getting the equilibrium values also. So ultimately, in this part of the study, what we concluded is the sorbent studies at high temperature carbon capture, the optimal set of parameters have been obtained, like around 400 degrees Celsius, 2-hour duration, 10 grams of adsorbent, and the sorbent composition, as I told you, that CaO, MgO, with 40% coal fly ash, that has given the best capture value, and the material is found to be stable at 250 cycles. And even the thermodynamics also, we understood that the nature of the thermodynamics is favorable in terms of its spontaneous nature. And as I told you, the second part of the study is, instead of using the coal fly ash directly, we also have done some studies wherein from the coal fly ash, we derived certain materials like NAA, which is a type of zeolite. And again, ZIF8 is one more MOF type of thing, metal organic. It is one type of metal organic framework, which is called zeolite imidazole framework 8. And that is combined with NAA, which is taken from the coal fly ash. So, and we are done in actually getting that ZIF8 composite with NAA. We are done in 3 ways. One is called in situ. The second one is called physical binding. The third one is called the simultaneous synthesis. The beautiful thing that we observed here is, it's not only about the material like, ZIF8 in a combination of NAA. That itself is not enough. Actually, the way that this composite is getting manufactured or synthesized also play a great role. That's a beautiful observation. For example, there are 3 ways. One thing is, suppose there is A and B. I want to have a composite of AB. There are 3 ways of doing: taking A, taking B, and mixing. That is called physical mixing or blending. That is not a perfect way of doing, and the material that is actually synthesized using the blending is found to be relatively less efficient. The second one is simultaneous synthesis. Simultaneous synthesis means there is a single beaker where all the materials that are required to synthesize A and all the materials that are required to synthesize B, they are dumped inside the reactor or a beaker, and they are mixed up. Then we'll get A, there we'll get B simultaneously. That is called simultaneous synthesis. And this particular simultaneous synthesis method is found to be better than the physical blending. But the beautiful thing that we found is that in situ method. In situ method means, in that A and B, we try to take, say, A as a source. In that A, in the environment of A, we try to synthesize B, keeping that A as the ambience. So that is what is called in situ method. So this particular method is proved to be very beneficial. If you look at, we got 3.48 in this in situ method. We got a capture value of 3.48, whereas the physical bending we got 2.38, and simultaneous synthesis got only 1.63. So my advice to all the researchers here, people might be working in different topics, the synthesis method also plays a role. It's not about only the components that you are trying to use there, how you are using the components. Sometimes whether A is mixed to B or B is mixed to A, that also matters. And the sequence of adding also matters. So what's the sequence? Whether you are adding A plus B plus C or C plus B plus A. So even the sequence also matters. That the way that they are mixing also is matter, because that will try to demonstrate or show how effectively we are trying to synthesize, especially the composite materials. And again, this is about process optimization that we have done using the ZIF8 in combination with NAA. And these materials have been synthesized, let me tell you, from the coal fly ash only. And the right side is a typical response surface contour, 3-dimensional figure, which can directly give the effect of temperature, pressure on the carbon capture. Normally, a graph can give a typical 2-dimensional graph will give the effect of one parameter on the second parameter. It's only 2 parameters. But these are the 3-dimensional contours where the temperature, pressure, the effect of two parameters will be shown on the carbon capture value. So from this, we can clearly understand that as the temperature is increasing, the capture value is decreasing, because if you look at the slope of the contour, it's lowering up. And if I try to look at the pressure thing, as I increase the pressure, the carbon capture value is increasing. So this particular thing is clearly observed. And in that the matrix, the table that is clearly shown, where again this is the experimental design that we got from response surface methodology, the central composite design, where we varied the temperature, pressure, and time of carbonation, and we got the carbon capture values which are listed. And if you look at the highest value that we got is 6.63 millimole per gram using this particular method. This is not a coal fly ash which is directly used. And also, let me tell you, this capture is not a high temperature capture. In the first part of the study, the studies were done at a very high temperature, like 400, 500 degrees Celsius. But if you look at the temperature column in the second column here, this is a moderate temperature, 40, 50, 60, and all that, not more than. So overall temperature is a moderate temperature carbon capture, because this NAA, zeolites, and zips cannot withstand very, very high temperatures. And again, we developed, so from this RSM model, we'll get a model there. The beauty of RSM is we also get a model. That means it will generate an equation wherein, for example, there are three important parameters like temperature, pressure, and the carbonation time, like A, B, C. It will generate an equation with that A, B, and C, where if I substitute the values of A, B, and C, I can get my capture value directly. That's the beauty of this. It will generate a model. And again, we got a model, and we use that, and we compared the model values with experimental values, and they are found to be very close, which implies the RSM model is working fine. So as per the model, it is 5.12 as per the model, and experimental value is 4.88. It's a marginal difference is there. So that means my RSM model is perfectly working fine. And coming to the characterization, anything to understand the process, what actually happening to the materials at a micro level, whether the material is rough, or is it as the molecules are smooth in texture or rough in texture, is it rod-like or granules type or spherical spheroids or all, or something like a flake-like structures. So we do the some studies, and we found that there is a consistency, there is a uniformity, which implies our synthesis protocol is working fine. And even our crystalline, the right hand side pictures, where the tall peaks clearly indicate that my material is perfectly crystalline in nature. It's structurally integrated, it's working fine. And even we have done that isotherm studies also, where we have done the pressure studies, and then for all the materials that we synthesized. And again, we have done one more level. We of course modified that material with even TEPA. TEPA is one type of amine, which is tetraethylene pentamine. And we found that by adding this amine, we got the capture value increasing. And up to 40%, if you try to look at 40% TEPA modified that zip rate at NAA, the capture value is found to increase from say 3.8 to say 5 point something. And so, and it's also flattening. That means beyond certain thing, it will not yield a greater result. So there's always an optimum percentage of TEPA that can be added. And by adding this, the amines, that means we are trying to modify by creating more of the active sites. The active sites are created, thereby the carbon dioxide molecules can combine and can come and sit on the molecules and sites. And also the affinity part. Sometimes the affinity also will increase because of this modification. That means the attraction of the carbon dioxide with the adsorbent, that particular pull also gets increased. And even, of course, the effect of temperature also is studied. Definitely, as up to certain temperature is found to increase, and beyond that, if the carbon capture value is decreasing, that's clearly indicating it's exothermic in nature. And we tested various kinetic models like pseudo first order, pseudo second order, Avrami model, Yelovich model, Weber Morris model, to understand what is that. Is it a first order or a second order, or is it a reaction controlled? Is it a diffusion controlled? Because for carbon dioxide to get and sit on the adsorbent, there is a diffusion. Molecules, first of all, CO2 has to come from the bulk gas, and that has to come onto the adsorbent surface. And within the adsorbent also, it has to penetrate through the pores. And whenever the carbon dioxide has to penetrate to the force of the adsorbent, it has to withstand the resistances that is called diffusional resistance. So whether the intraparticle diffusional resistance is more or is it a reaction control? So we can easily find using the kinetic modeling. And from this, we can say that the R square value, which is the last column, R square value for Avrami model is 0.99, which is very, very high, which is close to 1. Whenever R square value is very, very high, that means that is a better fit, which implies Avrami model, where there is a combination of the physisorption as well as a chemisorption is a consistent model. And we have done the adsorption studies of this particular at various pressures. We studied to get the isotherms. To understand what is the type of isotherm, we need to study the effect of pressure also. So to whether it's a physisorption or a chemisorption or a combination, or is it a crystalline nature type of thing? So we do that studies, and we try to study at the various isotherm modeling like SIPS isotherm, say the Toth isotherm, of course, Langmuir and Friendlich and all that. We have that again R square value for various pressures, and we found that the SIPS adsorption modeling explained the data very well when compared to the other models. So 0.999, that the red line, that red thing, that means that SIPS isotherm, which is indicating again there is a physisorption, there is a chemisorption, there is a crystallization also in place there. So it's a heterogeneous type of a phenomenon that is happening in the carbon dioxide capture. So that is validated and verified by fitting my experimental data with various models. And also we calculated what is the heat of adsorption. Whenever there is an adsorption, since we know that it's exothermic in nature, some heat is evolved. And we found that the amount of heat that is evolved is minus 11 kilojoules per mole. And according to the value of this heat of adsorption also, we can predict what's the nature of adsorption. Is it a physical, more of physical in nature, more of chemical in nature, or is it that means physisorption or chemisorption or in between, something like that? Because there are few, say, the thumb rules about the heats of adsorption versus the nature of the adsorption, the heat of adsorption versus the nature of adsorption. And we studied the thermal stability, the stability studies up to 50 cycles. And we found that the material is perfectly stable up to 50 cycles with very marginal attrition in the capture value. So with this, we clearly understand that the TEPA modified ZIP8 with NAA is giving a very good one. Avrami model is giving a better fit. SIPS adsorption isotherm is again fitting the data well. The heat of adsorption is found to be minus 11.8 kilojoules per mole. And we got ZIP8 is stable up to 50 cycles, and which is having 92% of the initial, whatever that adsorption capacity the material showed at the end of the first cycle. Even at the end of 50 cycles also, 92% of the performance has been demonstrated. And apart from that, we also, in the recent past, we are also doing some studies on direct air capture. That means here the amount of CO2 that is present in the air is very, very low. So to capture the CO2, which is present in a very small quantity, is really a challenge. For example, if I try to make the flue gas having a 30%, 40% CO2, capturing that CO2 is relatively easy when compared to capturing the CO2 in air, because in the air it is mostly N2 and O2, and the CO2 present is very, very low. And to pull that CO2 out, we require mature technology, we require good process control and all that. So we tried bimetallic zips, various types of copper, BCU, BTC, activated carbon with that. We synthesized in various methods by using solvent-free method or wet impregnation method. And we found that the bimetallic zip, CuZn zip 8, in the ratio of 1:2, which is found to be microporous, it has given a capture value of 0.34. Let me tell you, we cannot expect very, very high capture values for a direct air capture, because that's very, very difficult, because amount of CO2 present is very, very low. So even if you can do some amount of capture also, it is significantly important there. So this is again for that material that we use, like bimetallic zip. We have done the morphological studies using SEM. We have done the FTIR study to understand about various the functional groups that are incorporated there. And we have done the XRD studies to understand about the crystalline nature of the adsorbent. And also we have done some isotope studies also to understand about the material nature. And here also we have done use the process optimization by using the RSM. We have done the similar approach of kinetic modeling and isotope modeling. And we also found that cycle stability up to 10 cycles. And bimetallic zips as fitting the Elovich model to the best way, which is 0.99. And then, so the adsorbent selected was, the characterization was fantastic. And bimetallic zip at the optimal conditions has given the capture of 1.1 milligram per gram, which is coming to in terms of millimole, it is 0.348 or so. Experimental design was designed by the box Benken model. The Elovich model provided the best fit for the kinetics, and it also showed excellent stability up to 10 cycles. All these works that I presented now, they are published in highly reputed journals and they are well cited. And in future, as we know, the various things are there. First of all, the synthesis of the materials, we need to have high throughput synthesis, because if I want to commercialize anything, in lab, I require only a few grams of the material of adsorbent. But if I want to scale it up, I require kgs of material. So to suppose in to synthesize few grams of the material in the lab, it will take 1 to 2 days. So we cannot, that means for preparing 1 kg or 2 kg, I need to develop something like high throughput synthesis method, large scale synthesis protocol. And apart from that, we need to integrate the carbon dioxide capture with the utilization. It's not only about the carbon dioxide being captured, we need to ensure that the captured carbon dioxide is converted to some useful chemicals. So that also has to be done. And also in terms of regeneration, since regeneration requires high temperatures and high energies, instead of, we can use some renewable energy options like solar energy or tidal energy or some other energy, wherein the cost it can be leading to a overall sustainable nature or a green nature of say operation. It makes the process overall green in nature. And the scale up studies have to be done. As I told you, the large scale adsorbent synthesis, and the reactor, instead of a lab scale reactor, it has to be scaled up to pilot scale, pre-pilot scale, and then the integrating with the industry. So these are the various publications that we published in various journals. Apart from, of course, apart from this, there are many other articles. These are only selected few publications in this carbon capture. So these are some of the references that we seen that. So thank you. With this, I conclude my presentation on the carbon capture, which is a potential tool to address the global warming. Now, questions. If anybody has any questions, please feel free to.
So I have one doubt. You have used that box can design for designing your experiment. Why
Yes.
you chosen that box can design in rather than central composite design?
No, we have used the central composite design also. Only in the recent thing we
Which one?
compared,
Which
because
design is giving more accuracy, sir? Whether box can
no,
or central
both are
composite?
equal. I can say both are equally good. Only to maintain novelty, because we have done some sufficient publications using CCD. We thought of making some change in that, and so we have gone for that. Both are equally good.
Finally, we are getting optimized result in that RSM.
Yes. Yeah. In the
How
RSM, we'll
much?
get the, yes.
How much percentage that results are reliable? What about the error, plus or minus variations
No,
from experimental results?
the what we found is the variation is less than 10%. As I clearly showed in my one of the slides there, the model validation and the experimental results are perfectly fitting with a variation of only less than 10%. In
Is
most of the
this
studies, actually,
acceptable,
I've
sir?
been used.
Actually,
Yeah, I've
plus
been.
or minus 5% is acceptable for
Yeah. I think
finding any
this.
correlations, but this things gives a 10% variation means not at all
No,
accepted
not
based on some standard, right?
not 10%. I think it's 3.44. I think I've shown some value. It is very much as in the acceptable limit. It is very much within the acceptable limit in terms of statistics. It's a very marginal difference. It's almost coinciding with the predicted values versus your experimental value. If I go back to the slide, where is the slide that is showing? I think the model value versus this. Let me go back.
Sir, I have another doubt. Why we have to go for RSM rather than some algorithm? Because nowadays many algorithms are available that is giving more better accurate prediction than RSM.
Now, people are now moving towards AI, machine learning. Okay,
Yes.
people are now moving towards machine learning. I think that is the next level. Now, RSM is being used, has been widely used now. Now, the latest trend is people are now using, as you rightly pointed out, the machine learning models to design the experiments. We can incorporate the machine learning thing also, but to have the validation, we can have a RSM in combination with the machine learning to start with. Then once we get the comparable results, I think we can go on with the machine learning. Because that is, people are yet to start now. People are just now moving towards the machine learning.
Sir, this is Fanidhar from Bangalore.
Yeah.
I'm basically from electrical department, sir. So, what is the present status of carbon capturing practices in our real life?
People are
Status.
actually, one thing is because I'm guiding, because Bitspilani is well known for industrial programs. We conduct programs for various industry people. That's called work integrated learning programs. And I guide the projects also. I am the mentor for the projects. And there are projects which are people are working towards reducing the carbon footprint. Right now, the focus is mostly on trying to use trying to reduce the power consumption. Trying to reduce the power consumption is one target that they are doing. Second thing that they are trying to move towards the renewable energy sources. Instead of using the thermal power, they are trying to use the renewable energy sources. The third one is they are trying to bring in some changes in the process itself to try to make the process less polluting. But integrating the carbon capture technology as such into the industry, that will take some time. As I told you, it's not economically viable as of now, unless until the carbon dioxide capture is integrated with the utilization. But people are trying towards reduce the carbon footprint by trying to reduce the energy consumption in various ways. Did I answer your question?
Yes, sir. Thank you, sir.
This is Ilampuran from Bharat Institute of Higher Education and Research,
Okay.
Chennai. And I would like to know about the references, which is actually giving various types of carbon capture. In the sense, we should, that is, I would like to have different types in the sense, it both, what do you call it as artificially made as well as whatever the biological perspective we have for the carbon capture. Do you have those references so that
reference. You mean the reference in the sense? Are you asking for articles?
Yes, articles which has been published and
lots of articles. If you look at carbon capture, lots of. What is the research database that you're using in your institute?
Yeah, we have a Scopus.
Yeah,
and that is
yeah.
a BECS. One of the thing I have taken as a reference for actually for reducing carbon footprint in case of transformer. Basically, I'm an electrical engineer.
Okay.
But I would like to know, is there any other chemical way of capturing the carbon and storing?
That's what, whatever that I presented is a chemical way.
Yeah.
Whatever I presented is by using absorption, by using solvents, by using adsorbents through adsorption. Whatever I presented today is only through the chemical means.
Yeah,
as you pointed out is about the biological mean. That's basically the sequestration. That is not a carbon dioxide capture. Technically, it is called as a sequestration. That means by using algae and all that, CO2 molecules will be taken inside, and this algae and all will be acting like a sink.
No, actually, you meant to say that it has been captured and it has been disposed of somewhere, right?
Yes.
But what I am asking is whether that carbon, like if you are planting trees, it is like carbon neutrality, which will absorb and transform it into some useful energy. Is there any other methodology which is available at present, which you have been?
Actually, we are working on, of course, it is not integrated. Apart from the carbon dioxide capture, we are also working on carbon dioxide methanation. We are working on converting the CO2 to the methane. Methane is a clean fuel. So CO2 methanation using lots of, we developed nanomaterials. We have developed a nano composites and we got a project from DST and that is on carbon dioxide converting to methane, which is a clean fuel and which is a less powerful, less prominent greenhouse gas. So methane can be directly used as a clean fuel. But only thing is integrating the capture with that methanation has to be done. That is our next level, and we are going to do that.
Okay, thank you for your clarification.
Somebody
Thank
is
you,
asking
sir.
some Narendra
Sir,
Modi.
they are talking, sir. They are talking, not asking any question.
Oh, okay.
Okay,
Then.
sir. Okay.
Thank you. Thank you very much.
Thank you.
Okay.
Sir, myself, Dr. Sandeep Kunar. I am giving the good evening to all. I am giving the brief introduction. Dr. D. Jai Krishna sir. D. Jai Krishna sir is a professor in the Department of Mechanical Engineering at the National Institute of Technology, Warangal. With over 2 decades of experience in academic, research, and industry, he earned his PhD from IIT Madras, has held position at BITS Pilani, Texas A&M University and General Motors Technical Center, Bengaluru. Expertise spans phase change materials, thermal energy storage, computational fluid dynamics, thermal management of electronic and battery system, solar energy utilization, and thermal desalination. Dr. Professor Jai Krishna sir has guided a large number of PhD, MTech, and BTech students, published extensively in reputed international journals, hold granted different kind of patents, and successfully completed sponsored research and consultancy project. In addition to delivering numerous invited lectures and organizing academic programs in NIT, and he provided his valuable lectures in different reputed organizations also. Thank you, sir. Dr. Jai Krishna, sir, I request you to continue your lecture, sir.
Thank you very much, sir, for a very nice intro. First of all, good evening to one and all, and welcome to this Atal Online 6-day faculty development program, which is totally based on AI-powered optimization strategies for sustainable electric and fuel cell vehicles. And as it was mentioned, the thrust areas pertaining to this particular FDP is towards energy, sustainability, and climate change. My topic will be more towards thermal energy storage, and I'll be emphasizing more on phase change materials. What I'll be doing is, along with introduction, I'll be parallelly taking it not only from thermal energy storage point of view, because these phase change materials are being extensively utilized in several applications. So I thought it will be a good idea in this particular platform to even discuss few more applications of phase change materials. Okay, so you can see towards your left, there is some liquid is being poured and it is getting solidified. Okay, then we can say that thing as a solidification process. And at the bottom, you can see there is a candle. This is the best example that we can cite for phase change process itself, because usually it is a wax, and when you light the candle, that heat is transferred to the wax, which is getting melted, and because of gravity, this melted liquid PCM is coming down and it is exchanging heat to the surrounding air, which is at low temperature, and again it is getting solidified. So you can see two important aspects. One is melting and another one is solidification over here. And if you can see towards your right, the various pollutants that are being emitted from industry. This is one is industrial sector, and as well as this automobile sector, where we dump so much of chemicals, pollutants into the air, where we do have primary pollutants, and these pollutants react at different conditions and we get secondary pollutants also. And obviously everyone is very much aware of this, which is nothing but consequences is the sea level rises and the land that we have is getting eroded. So in line to this, I would like to proceed further. So the organization of my today's presentation is in this way. First, I'll be briefly introducing what is the necessary for us to go for thermal energy storage. And next, among various thermal energy storage methods or methodologies we have, I'll be focusing or emphasizing more on latent heat storage materials. And then I'll do like classification and selection criteria, because this is one of the very important aspect. This, as this phase change materials can be used for several applications. need not be for thermal energy storage itself. This classification and selection criteria becomes like an important chunk. Next, as I mentioned, I'll be going through the applications part and some of the important aspects like compatibility, phase segregation, thermal reliability issues. These things will be discussed. Next, okay, if someone wants to start some research on like phase change materials and how, okay, we do have some data and now you came out with some phase change materials and you need to find like to its suitability, to what extent it works. So there is a need for you to go for the measurement of these thermophysical properties. So finally, I'll be briefly concluding this particular presentation. Coming back to the introduction part, you can see everyone is very much aware of global warming. So whatever solar radiation that is reaching the Earth's surface, particular amount gets absorbed and nearly 30% re-radiates back to the atmosphere. So now this 30% you can say in general as a Earth's albedo. So now what is happening is this whatever absorbed radiation is that the Earth starts radiating back. So if you just take the wavelength for solar radiation, obviously it varies from 0 to that of infinity. And the radiation which is of shorter wavelength can easily penetrate through these gases which are present in our atmosphere. And once the re-radiated radiation from the Earth, as it is of larger wavelength, this radiation cannot go back to the space. Why? Because this acts as a like an opaque medium for these gases to go out. So the average temperature increases. This is like these things we have been reading. Now, if you say about greenhouse gases, we mostly mention about carbon dioxide. But carbon dioxide is not the only greenhouse gas. We do have other greenhouse gases like water vapor, nitrous oxide, methane, carbon dioxide, and so on. But we project every time CO2. The main reason for projecting or highlighting CO2 is that out of the various greenhouse gases that are available, CO2 contribution is high, which is something like nearly 60%. So, and one more thing. So the question comes, are these greenhouse gases not with us earlier before industrialization or like before we started dumping all these pollutants into the atmosphere? Yes, these greenhouse gases are there earlier also, but its percentage is about 1%. Now the thing is, as this percentage is increasing, this is giving us to like global warming. That means the average temperature of the Earth is increasing. And one more thing is that actually this nature is perfectly balanced and it has given things in such a way like this, it made our life in a very comfortable manner. Why? Because if these greenhouse gases are not there, our Earth will be too cold to live. Something like whatever temperature we are having now, we'll be having a temperature which is nearly 30 degrees less than what we are having now. So the thing is that as we are dumping more and more pollutants, obviously it is leading to the increase in average temperature of the Earth. See, this is not only one aspect. Earlier, we used to simply mention that the ice near the poles is getting melted and the sea level is rising. That is not the only threat. People now started experiencing other things. Why? Because in certain regions near the poles and Serbia, what happened is there were several viruses which were trapped in the ice itself. Now, this as the ice is getting melted, all these viruses and several infections are like going around different parts of the world, and this is also causing several consequences. So there is an utmost need for us to seriously tackle this particular situation of global warming. Now, there is always some kind of contradiction. Usually, you can broadly classify into two groups. One group says like usually this is the tendency of the Earth itself, where the Earth average temperature increases and slowly it again comes down. But scientifically, by taking certain samples near the poles and so on, what people could find is the Earth's average temperature is correlated, or it is like depending on it depends upon the percentage of CO2. As you can see in the slide here, as with the increase in CO2, the average temperature also there was an increasing trend. So what we can say is like there is a need for us to reduce this CO2 emissions. Now, what is that? What are the consequences we can have? This is the picture, or like details were taken from official Twitter site in UN climate change. For example, if an average temperature of the Earth is increasing by 1.5 degrees C, then there is a 3% probability that we can have like Arctic region which is free from ice. And obviously, because of this, there can be an average drought about some 2 months. And now 4% of the mammals will lose their habitat. In the same way, if it is 3 degrees centigrade, that means 1.5, you add 1.5 more temperature, then there is a probability increases in a very significant manner, which becomes like 63%. And we may have an average drought of 10 months. And what is going to happen because of this? 41% of the mammals will lose their habitat. This is like one very important aspect. Now, let us see what are the CO2 emissions, which country is releasing how much, what is the amount of CO2 emissions that we can find around us. So whatever you can see on this slide, there are various countries which are given, and China contributes around like 11,950 MT CO2, means megatons of carbon dioxide equivalent, and India stands in the third position, which India contributes something like around 3,219 megatons of carbon dioxide equivalent. So if you just observe, 34% China accounts for like a huge chunk, and which leads to around 1/3 of global emissions. And slowly we can observe like even in India also, especially when we come across this winter, especially Delhi is what stands in the news. The air quality index significantly dips down, which crosses around 350 also, is highly dangerous for us. Now, if you see like what are the like source of for the CO2 emissions? So coal, if you just take from the Indian context, why? Because whatever power that we are getting from thermal power, we mostly get from thermal power plants. So we generally consume something like whatever power that we are getting, like energy is being which is utilized. The major source is coal, which leads to like a huge number of pollutants, and its contribution is 77%. And next comes oil, and next comes gas. And if you take the statistics for the complete world, coal contribution is around 49%, oil is 29%, and gas is 22%. In earlier years, what happened is even this problem like smog, photochemical smog, and presence of ozone, peroxyethyl nitrate, and all these unburnt hydrocarbons and all these pollutants were observed in Europe. So, but now if you observe the latest trend, these emissions were significantly reduced. Why? Because they started going for much cleaner fuels, and they started moving more towards renewable energy sources. So now the question comes, we do have several renewable energy sources like solar, wind, biomass, geothermal energy, ocean thermal energy, and so on. But I would like to project on solar. Why? Because let us see some statistics, few figures. Like if you see like the amount of radiation, solar energy that is reaching the earth is around 1.5 into 10 power 18 kilowatt hour. And if you just take, this is a little old value, it is around 1.5 into 10 power 14. So approximately, if we can effectively utilize, now it might be slightly more. This is the old data I had. So it is around 0.1%, which can meet our like requirements. So, and one more thing, if you just take various losses, and finally, about 1 kilowatt per meter square of solar radiation is reaching the Earth's surface. Okay, based upon this, if you just observe, we can effectively utilize this solar radiation. And if you just see the distribution of solar radiation, this is solar like as per the magnitude or intensity of solar radiation, it is given in terms of contours. You can see even if you take different parts of the world, this radiation is not like uniformly distributed. It is more intensity of radiation you can find in certain locations, and other locations you can hardly have sunshine. Now let us see like from what is the percentage of wind and solar in electricity production. If you just observe, Denmark stands first, like the countries where significant of CO2 emissions were given. Those countries are not even in the list. So especially from European countries, they are moving more towards more and more renewable energy. And the Denmark contributes around 69.5. Whatever I am saying is only the contribution from solar and wind alone. So 70% share of solar and wind in Denmark, Denmark's power mix, like you, because whatever power that we need, we get these things from different sources. You just imagine 70% they are getting from solar and wind alone. Now, what is the contribution from Indian context? It is around 12%. So let us see a few more things. So if you take the Indian context, solar contribution is 6.8%, and wind is 4.3%, and rest of the approaches for methods that we had for tapping this electricity or for electrical production, electricity production is around 88.8%. So, but actually, if you see, we are very much blessed with a good amount of sunshine, and even India is blessed with a huge coastal line. So we can effectively tap both this wind as well as solar energy. So what we had is like approximately 35.6 gigawatts. We do have like installed capacity, and like it is expected to increase, and further we are moving towards more solar energy, like by installing solar PV and so on. See, like what we can see from here is we could observe that we do have a very good sunshine, and the question is now why we are what kind of problems do we have, why we have been not effectively utilizing this solar energy. Why? Because the whatever radiation that we are having, the density or intensity of radiation is low. That means the radiation that is reaching the Earth's surface is low. Another thing is we do have temporal variations. That means assume that you are having now a bright sunny day, and maybe next hour or the coming hours we may have the passing cloud, and we may not have that much solar radiation. That means it is totally unpredictable. So, and one more thing, as I told, this radiation is not equally distributed. Certain parts of the world you do have a very good sunshine, and certain parts you hardly have that. So now the question is how these problems can be overcome, like what kind of solutions we need. One is that you just go for to overcome the first problem, you use some solar thermal devices or like solar devices, where if the intensity is less, you concentrate the solar radiation and utilize for some purpose. Another thing is because of the temporal variations, this is the main thing that is being hindering the utilization of renewable energy sources. So what is the solution for it? You need to go for an effective conversion mechanism and storage methodology by which you can effectively tap these renewable energies, especially like solar energy. And one more thing, certain parts of the country you have good amount of sunshine, and certain parts of the world like you may not be having this. So what you do is you tap this solar energy, convert to some transportation fuel like hydrogen, and you supply wherever this solar radiation is not there. So that is why if we can focus on these three areas, we can significantly reduce the CO2 emissions. So if you take an annual solar radiation of about 1700 kilowatt hour meter square and take a collector efficiency about 5%, the area that you need collecting concentrating area or like collecting area that you need is around 1100 by 1100 kilometer square. And if you just take this is only like 2.4%. And if you take only about Earth's surface, which is covered with the land, which comes to be 8.1%. Now the question is, how do you use this solar energy? Generally, if you say solar energy, most of us are an impression that solar energy can be utilized only by means of photovoltaic panel. That is not the case. So actually, you can. One thing is a very straightforward thing is that you use a photovoltaic panel and directly convert to electricity, and you store this in terms of like either batteries, electrochemical energy storage. Other thing is that you go for solar thermal. So you tap this solar energy in the form of heat and you store in some materials. That is what our focus is going to be, and utilize this heat for different requirements. And obviously, based upon the temperature range that we have, you can classify into space, water heating, and even if you are able to attain further higher temperatures, something like 500 to 3000 degrees centigrade, you can even use for power generation. So that is one. Obviously, you need to have some device. Now, if you see conversion and storage, whatever left you are seeing, we are placing solar photovoltaic panel, and that energy is being converted into electrical energy. It is being stored in the battery, and now as per your requirement, either these panels can be directly connected to the grid, or it can be stored in a electrical battery, and as per our requirement, we can make use of it. And towards your right, one thing that we can see here is one is sensible heat storage, and the next one is thermochemical energy storage, which I'll be discussing further. So depending upon your requirement, what is the energy density, in the sense how much amount of heat that you can store for a given mass or given volume, based upon that also our selection will be depending on. So I'll be further discussing about the selection procedure for it. So another thing that we can have is, as of now, just before I could hear Professor Sridhar, what he was saying is generally it is like carbon capture and everything. He was saying like whatever thermal energy that we are supplying, we can make use of renewable energy. So what we can do here is we can make use of solar thermal energy and make it much more efficient. So if you just take and let us see more about like how can you have whatever solar energy that is being tapped can be used as a transportation fuel. Like most of us are very much aware, there is some process called steam reforming. So what happens here is this methane, by exposing to steam, it converts to hydrogen. This is a very common method that we generally use for hydrogen production. Please do understand, this is not the only method. We do have other methods also, so like solar methane cracking and other methods, electrolysis also. During the electrolysis process also, we can make use of solar energy and even get the hydrogen. So ultimately, whatever hydrogen that we are getting, if we are using this in the case of fuel cell, obviously the end product that we get is nothing but steam, and obviously we'll get electricity out of it. So this can be used for electricity production, or like even for the transportation for automobiles and so on. So now coming back to why is thermal energy? So why don't we focus on any other forms of energy? If you just see, depending upon the temperature range, low temperature, you can classify less than 100, medium temperature 100 to 400, and high temperature means let us classify it as like a more than 400 degrees C. If you see the total energy consumption, like from the industrial context point of view, 74% of industrial energy consumption is met by the process of heat demand. So, which is a huge thing. So, if you obviously we can say this heat energy as a low grade energy, and instead of again converting to electricity and again convert electricity to the heat energy, it is a very inefficient process. So, by somehow by some means, if you can effectively and efficiently store this thermal energy, you can see like 74%, which what we are doing now is we are just burning some fossil fuels, or certain parts we are burning this biomass, and we are trying to get this heat energy. But if you can effectively store, and by utilizing this renewable energy, it is going to be a very promising one. Let us see further. So if you see solar, like thermal energy storage, we can broadly classify into three types. One is sensible heat storage, another thing is latent heat storage, and the third you can classify under thermochemical energy storage. So now, what is sensible heat? So the amount of, if for example you are exposing some object to a high temperature, the amount of heat stored can be given as mCp delta T, where m is the mass, Cp is nothing but the specific heat, and delta T is nothing but whatever rising temperature you have. I just provided few things here. One is, this is nothing but some metal matrix. It can be whatever wire that is wound, or it can be a metal foam. For example, let us take, everyone might have seen, we get some kind of scrap from like certain machining operations. If you do lathe and any other workshop, we do get some scrap, right? You can collect all the scrap, and that also you can say it as a metal foam. So like, because it is a metal foam, why? Because you can have, why, high specific heat should be there, and thermal conductivity is also high. This is one such method by which you can store this heat energy. Another thing is like, is a very like environmental friendly, as well as the economics point of view, is also a very attractive option. This is a pebbles or rock bed. What we can do is, we can take a pit and simply fill that pit with these pebbles, whatever you are seeing over here, and you supply hot water, and because these pebbles will store the heat, and whenever you are in need of some heat energy, obviously there will be a very good insulation also. So whenever you are in need of this heat energy, you supply cold water and get the hot water back. This is a very simple way, and less expensive. So, and we usually, everyone might have seen this solar flat plate collector. Whatever it is given on the left top is evacuated tube collectors. So it is a higher version or efficient version of solar flat plate collectors, what we are seeing in the market. So usually what we usually do is, the water gets heated up and the hot water is stored in an insulation tank. Okay, so this is nothing but a sensible heat storage. And towards your right, what you can see is like a solar pond. So how the solar pond works is that you have three layers. One is a convective zone, which is considered to be like upper layer, where the concentration or density of this particular salt is less. Next, you do have a gradient. You can say that thing as a non-convective zone. And if you further come down, this is going to be a low convective zone. In this low convective zone only, heat will be stored. So one thing is that as you go from top to bottom, the density of this particular liquid, if you take as a brine solution, the concentration of this salt should be increased. Then what happens is, the heat energy gets trapped at the bottom, and now you circulate some, what I can say, some cold fluid, or some fluid which has a very low boiling point, and from this also we can generate electricity in the, like, by connecting through a Rankine cycle, we can tap this power. So one more thing is that, especially in Europe, heat energy will be stored on a seasonal basis. So when you have in summer, like a good amount of sunshine is available, so you have some collectors, and this hot water is being pumped to a particular depth. Usually, this under the ground, you should be having some permeable layer. So water is stored here. And next, when the winter comes, when the temperature of the surroundings drops, so now you circulate this cold water, and whatever heat energy that is trapped under, like you can get the hot water, and we can use for room heating purpose. That means we can even use this thermal energy on a seasonal basis also, not on a daily basis. So now the question is, how do we select a sensible heat storage material? Now, like we see so many like materials around us, maybe like dried leaves, dried branches, and we can have some waste, paper, and all the things. We can see certain things around us. So, can we use any material as sensible heat storage material? No. What? Because it meets certain like criteria. For example, its specific heat should be as high as possible, and it should be having high thermal conductivity, and it should be having high heat storage capacity. Heat storage capacity can be given as density into its specific heat. Along with these things, obviously, like the service or life of that particular material should be high, and it should not be corrosive, it should not be toxic, it should not be flammable at all, and it should be freely available, obviously. So now, in general, what happens is we do have so many examples like what I can say materials. So if you just see this one, now for example, if your application is 150 degrees centigrade, so water is one of the best sensible heat storage medium that we can use. Now the thing is, but if your temperature is at 150 degrees centigrade, you cannot use water as your heat storage medium. Why? Because water obviously converting to a vapor state. So the first important criteria is what is your temperature range of the application that you are considering. For example, if you are storing thermal energy and your application is less than 100 degrees centigrade, because at atmospheric pressure 1.013 bar, the saturation temperature that you have is 100 degrees centigrade. Now the thing is, like then only if it is less than 100, you can go for water as a heat storage medium. But let us take your application is something like 500 degrees centigrade or something like relatively high, around let us take 300 degrees centigrade. Then definitely we cannot go for water as your medium. So based upon the application temperature, then we need to select the sensible heat storage medium. That is one. And whatever materials that we are using, the density of those materials should be as high as possible, and obviously specific heat. So now there is something called energy density. That means amount of energy, heat energy you can store per unit volume. So what you need to do, first you need to check what is the temperature that you need to store the heat. And along with that, you do have n number of materials around you. So among these materials, which material will be having very high energy density? Like that we need to select. This is about sensible heat storage materials. So next is thermochemical energy storage. Now, along with phase change materials, researchers started utilizing thermochemical energy storage for especially power generation, especially solar thermal power generation. So let us try to have some insight about thermochemical energy storage. So let us take, you have two substances. A1 is one substance and A2. So now what is happening is, once you supply some heat, these substances get divided. Okay, it becomes like two different compounds. Now when you add these two compounds, obviously it should be generating heat, and this process should be reversible. For example, you can take magnesium sulfate heptahydrate, and to this, once you supply this heat, it splits to magnesium sulfate and water. And when you add these two things, it becomes an exothermic reaction. And with this process, we say Epsom salt, right? So this is nothing but magnesium sulfate heptahydrate. So this can store around 2.8 gigajoules per unit volume of heat energy. And one more important thing is that the reverse reaction is prevented by separating the products A1 and A2. For example, You have two compounds A1 and A2. Now, in order to separate these two compounds, what happens is you supply some heat. Now, the thing is, how do you keep it separated? So, once you supply some cold water or some cold fluid, this should automatically combine and it should be giving you heat. Actually, this is one of the difficulty that people are facing, and people are trying to streamline this so that we can effectively use for certain applications. And for some of the materials, or like whatever selection we are doing, we should select in such a way. So sometimes what happens is, as you are separating these compounds, by adding some catalyst, this should liberate some heat. Or for example, you are sending some cold fluid or cold water and are slightly reducing the pressure. This should be enough to liberate the heat. It should be like an exothermic reaction. Generally, chemical energy conversion has better energy storage performance efficiency than sensible and latent heat. But obviously, you need to select some materials in such a way with very less effort or very less challenge. It should be reversible in nature. So, in general, sensible heat thermochemical energy storage materials are used for high temperature applications. So, but there is a drawback with this one. So, usually, if you take solid gas thermochemical reactions, because in a gas it is in gaseous state, it has very poor heat and mass transfer rates. So, and which will lead to very low efficiency. So, certain things, still lot of work is being done, and still researchers are trying to get a very attractive solution for this. To cite some examples, if you can see ammonia and calcium carbonate, you can see, like, depending upon what temperatures that you are working on, you need to go for appropriate selection of the compounds. And you can see in the column also, it is energy density is also given. So one thing is that what is your temperature of application? That means what application you are looking for. Okay, so based upon the application, what compounds you are looking for. And obviously, if you are having some 4 or 5 compounds altogether, we have to check what compound is like having very high energy density. Obviously, it should not be toxic. It should be freely available. Like life should be good, and so on. Certain aspects need to be seriously looked in. So this is one of the very like upcoming field, especially for high temperature heat storage applications. One very good example, what people could find is ammonia. So whatever you are seeing here, this, let us take, this is a central receiver system or heliostat based central receiver system, where you can attain very high temperatures. So you have some working fluid here, and you are sending this heat energy to ammonia, and this ammonia splits to like nitrogen and hydrogen. And when you are actually trying to combine, this becomes like an exothermic reaction and liberates good amount of heat. And the temperature that you can have is around 400 to 500 degrees centigrade. And obviously, depending upon this temperature, depends upon what pressures are being maintained. Now, what we have seen is sensible heat storage materials and thermochemical energy storage. Now we have to see about phase change materials. So what I'll be dealing with is, like, along with certain introductory aspects of phase change materials, I'll be even giving some applications also. So usually, what is PCM? Full form is phase change materials. Latent heat storage uses phase change as a phase change process as a storage medium. So what is going to happen when heat is being absorbed? One phase is being converted to another phase, and it is regaining its original phase, means then there will be liberation of heat. So towards your left, you can see one thing. Let us take you take ice itself. Ice at atmospheric pressure, it starts melting at 0 degrees centigrade. So now let us take room temperature is 25. So 25 to 0 is sensible heat, and 0, which is in solid form, that is ice, again 0 to water, there is a latent heat. You say that particular process as melting. And now again water at 0 degrees centigrade, to room temperature is 25 degrees centigrade is there. Okay, so this is again sensible heat. So when we are selecting a PCM, it is inevitable for us, like just to only consider phase change. Along with that, there will be a sensible heat portion also. So towards your right, I am trying to show you some picture where this solidification process is taking place. So you can see initial crystal is formed, and it slowly starts expanding, like covering all the domain. So it totally becomes like a solidified. So this is having like huge number of applications. Now, based upon what is the temperature range that we are looking for, we do have n number of materials. Okay, it can be like sensible heat storage materials, and it can be like phase change materials. Under in phase change materials itself, you do have a wide classification. So it is very much important for us. If you can see, just before I told you, in thermochemical energy storage, there is something called magnesium sulfate heptahydrate, MgSO4 7H2O I did mention. So now its application is like it has very high energy density, but the operating temperature range is also very high. So based upon our application, we need to go for the selection of a suitable material. Now, so why, for example, what we can see is, okay, let us take there is some complexity and still lot of work need to be done in thermochemical energy storage. If we start comparing sensible heat storage and phase change materials, what differences we have? Phase change materials or latent heat storage materials can store good amount of energy in a given volume. What does it mean? Like it has very high energy density when compared to sensible heat. If you just see, compare it is like a overall comparison. The volume that it requires for phase change materials is 5 to 14 times less when compared to sensible heat storage system materials. So that means you have some design or some heat storage system. Instead of using sensible heat storage materials, just imagine your size will significantly come down by 5 to 14 times. So your energy, as the energy density is becoming more, your system becomes like more compact. One of the beauty or advantages that we have is small temperature change for storing and releasing heat. That means if you have a system where you need to maintain a required temperature, okay, nearly constant temperature, you cannot have exactly the same temperature, nearly constant temperature. So phase change materials are considered to be very, very promising. Because of this reason and high energy density, phase change materials are being used in several applications. For example, just to in terms of like values, quantitative comparison, if you just take storage of mass, and if you are storing something like 10 power 6 kilojoules, if you take water, 67,000 kg of rock you need. And if you take phase change materials, and obviously I'll just give the classification, there is organic, inorganic, and nucleic. It is around 5,300 kgs. This is what the mass that you need. And if you just see the volume in terms of meter cube for storing 10 power 6 kilojoules of heat energy, if rock that is needed is around 30, just imagine, and the two organic PCMs, it is 6.6. And the inorganic PCM, it is much less. So this is what we can see is, because of its very high energy density and heat storage and release at nearly the constant temperature, these are phase change materials are considered to be really promising option for several applications. Now, if you see the classification, you can broadly classify phase change materials as gas liquid phase change material. For example, water, when you supply heat, it converts to vapor, gaseous state. And solid gas, let us take camphor, naphthalene balls, solid CO2 or dry ice. What happens is directly converts from solid when heat is supplied to it, or it is exposed to high temperature. When compared to its transition temperature, it directly converts from solid to gaseous phase. Another thing is solid liquid. Let us take ice to water. That means it is converting to solid phase to liquid phase. But one more thing is also there. Solid PCM is also there. You might be wondering, what is this? He is saying solid, and again other phase is also solid. Then how can it be a phase change material? That question, that kind of question may come to us. The thing that we need to understand here is, it is in solid form, but once we supply some heat, it goes from one crystalline structure to other crystalline structure. Okay, and once you expose that thing to some cold environment or lower temperature, it regains its original crystalline structure. And especially a lot of work is being done, especially on solid phase change materials. Let us take, we all can see our mobile phones, right? So mobile phones, obviously heat is one important criteria, and you cannot use other form of phase change materials. Why? Because again means you need to have some like covering, and where if it is converting to liquid state, the volume increases and several issues are there. So for those kind of applications, solid phase change materials will be a very promising option. But one of the drawback it has is it has very low thermal conductivities when compared to other things. Now the question comes, okay, let us take among solid liquid, gas liquid, solid gas, and solid. What phase change materials we need to go for? Definitely we can go only for solid liquid phase change materials. Why? For example, if you are having a gaseous phase, that means solid converting to gas and liquid converting to gas, one thing is that usually gases, everyone is very much aware of, gases take more volume. So when it is converting from one phase to gaseous phase, the volume requirement of your heat storage system will be very high. That is one reason. Another reason is that to regain its heat back, to retrieve or whatever heat that is being supplied, if you want to retrieve the heat back, you need to do some external work. Why? Because, for example, let us keep a very some water is flowing, or cold water is being is made to flow through the pipe, and there is a shell and tube heat exchanger around the pipe. You have some PCM where it is solid to gaseous form is there. Now, if you want to retrieve the heat back, we can observe that only it starts condensing, or it only starts crystallizing only at the surface. But because gas heat is in gaseous phase, so you need to pull back near to the cold surface, for which we need to do some external work. Because of these reasons, and again, if you see solid PCMs has very low latent heats. So that is why we have to go for solid liquid phase change materials. It does not mean that solid has does not have applications. We do have applications. One of the main problem is like the low latent heats and relatively low thermal conductivities. So, and if you see solid liquid phase change materials, you can have organic, inorganic, and eutectics. Obviously, organic means we can have paraffins, fatty acids, esters, alcohols, and so on. And again, inorganic, it can be any salts, metallic compounds, salt hydrates, and so on. And what do you mean by eutectics? Eutectics can be a combination of two PCMs. That means you can have two organic PCMs once it is mixed, and one or two inorganic PCMs. If you mix, it becomes an eutectic. Or if you are mixing one organic and one inorganic PCM, you can say that is also eutectic. Okay, so it can be of any combination. So why we go for this combination? For example, you are having some PCM1, which has very high latent heat, but its melting point and thermal conductivity is not as per your requirement. But you have a PCM2 where its latent heat is relatively okay and has high what I can say thermal conductivity. What you can do is you can blend it, maybe like 20%, 80%. It can be 50%, 50%. Several combinations are possible. Obviously, we need to do characterization. So now if you see, whatever PCMs that we have, it is not like universal. Obviously, certain class of PCMs do have advantages and certain things have like disadvantages also. Organic PCMs, if you just take, there are availability in a huge temperature range. And one more thing is that it is having a good compatibility. What do you mean by compatibility? For example, if you are using in a heat storage medium, this PCM should not corrode that container material. So that is what compatibility. And chemically stable. For example, if you are using now, let us take assume that we have 300 sunny days in a year, and let us assume an application of solar water heating system. So we are having one thermal cycle. Next question comes, what do you mean by one thermal cycle? That means you are supplying heat and PCM is converting to liquid state, and you are reutilizing the heat. Again, PCM is converting from liquid state to solid state. That is one heating cycle and one cooling cycle together. You can say it as a one thermal cycle. So in that context, if you assume that 300 sunny days are there, and each day if you are having one thermal cycle, you can estimate the life of your PCM. That means whatever performance you are having today, you may not have the same performance after 2 years. 2 years means, let us take 300 days per year, 300 into 2. Okay, that means 600 cycles. If usually what is observed is certain class of PCMs are good initially, and once you use for 1000 cycles, that means 1000 heating and cooling cycles or thermal cycles, the performance is coming down. That means, what do you mean by performance coming down? Means you are selecting a PCM based on its melting point. Now what is happening? Let us take it is at 50 degrees centigrade, but after maybe like 600 cycles, the melting point will not be 50. It will be either 45 or it is going to be 55. That means whatever selection you did, it may not work well. And one of the advantages of organic PCMs is high latent heat, and it is safe and non-reactive. Obviously, it is recyclable. It is more environmental friendly. So another thing that we have is demerits or disadvantages that we have is it has very low thermal conductivity. Relatively, heat storage capacity is low when compared to inorganic PCMs. And one more important thing, especially for certain class of PCMs, they are flammable. Especially, I'm going to tell in the later, maybe a couple of slides later, that we can use even PCMs for thermal management also. So when we are using certain for those kind of applications, we should be very careful in its selection. Obviously, cost. Now, what about inorganic? Relatively, its cost is low when compared to organic PCMs, and it has high sharp melting point. What do you mean by sharp melting point? What we generally think is, if you are selecting a PCM, even in literature or someone is addressing any PCM, what we say is its melting point is 50. But practically, it is not only 50. That means melting may start at 50 and it may end at 55. That means that delta T will be there, but it is not like exactly 50 will not be there. And its thermal conductivity is relatively high. Relatively high means if you take 0 0.2 watt per meter Kelvin for organic PCMs, it may have 0.7, 0.68, 0.8 or something. That much relatively in that way, inorganic PCM thermal conductivity is high. And when compared to organic PCMs, inorganic PCMs has very high latent heat. And one more thing, volume change. What do you mean by volume change? You are having a solid PCM. Now you are supplying heat. It is now converting to liquid state. So as the densities in solid state and liquid states are different, now what is going to happen? Obviously, mass is always conserved. Mass should be fixed. So whatever change in density will lead to change in volume. So this is one very important criteria for the selection of during the selection of heat storage system. Why? Because you design some system where it takes very less volume during solid, and if its volume change is high, it will sometimes the latent heat storage system may even burst also, may expand or like explode. So, and one more important thing that we have here is it's non-flammable when compared to organic PCM. And this is one of the very important aspect that one should seriously look in, especially when inorganic PCM is being selected. Supercooling. What do you mean by supercooling? For example, you have an application of 50 degrees centigrade. Now what should happen? So once you are supplying heat at nearly 50 degrees centigrade, PCM should be converting to liquid. Now once you try to retrieve the heat back, maybe you are trying to cool it at 50 degrees centigrade itself, it should start converting to solid state, but that will not happen. So that delta T, whatever it is there during solidification and during melting, you say that thing as a supercooling. Actually, this is one problem with inorganic PCMs. And one more important aspect is compatibility. That means most of the inorganic PCMs are highly corrosive. And sometimes to overcome this phase segregation effect, mutilating agents might be needed. So, and one more thing is that, so whatever disadvantages that we have in PCMs, if you are trying to overcome these disadvantages by adding two different PCMs, you say those things as eutectics. So you select the eutectics or like combination of this PCM in such a way, you have high melting point, high energy density is there. But one more thing is that because you do have n number of combinations in coming with the eutectics, relatively data is less. So several people are even working on different combinations of PCMs, and they're trying to come with different eutectic materials. So the question comes, how do we select a PCM? Okay, first and most important thing that we need to have is that we need to select in such a way your melting point of the PCM is in application temperature range. This is very, very important. Okay, so this is very important. Otherwise, what happens is whatever application that we are going for, let us take your application is 40 degrees centigrade and your PCM melting point is 50 degrees centigrade. Then that PCM will be very, very ineffective. Why? Because it's usually PCM's thermal conductivity is very low. Then it will not meet your requirement. And the next most important criteria is high latent heat. You have to select a PCM in such a way its latent heat is as high as possible. And next comes other things, small volume change, congruent melting, thermal conductivity should be high, it should be completely reversible. That means whatever things heat is being released and heat is being absorbed, even after certain number of cycles, it should be doing in the same manner. It should not be toxic, it should not be flammable, it should not be explosive. And one more thing is that compatibility. I'll be showing, I did come across certain observations. I'll be showing you in the coming slides. And economic criteria. You have promising features, properties, but ultimately its cost is very high. Then definitely we will not go for it. So it should be easily available. And one more thing is that cost point of view is also should be as low as possible. So for any application, not only for energy storage, for several applications, PCMs are being used. And we have to follow this selection criteria to have an efficient system. I just wanted to show you what way we can use these PCMs, especially for thermal energy storage. Generally, this is a solar water heating system. I hope everyone is very much aware of solar water heating system. And most of us will be an impression that, okay, if you are saying heat storage system, it is going to be a separate unit. So separate box will be there where you use some medium and you send some hot fluid. Heat is being stored in that medium, and again you will retrieve it when you are supplying some cold water. Most of us will be in particular impression, but it is not so. Now PCM even can be coupled with the solar thermal devices. The very common device that everyone is aware of is solar water heating system. So usually this is the left hand side wherever I am just keeping the mouse. You can see here, this is a flat plate collector, and on the top we do have this heat storage system. That means sensible heat storage medium where hot water is being stored. So this is for the procedure or the way in which heat is being stored by buoyancy, thermosiphon we say, because of the density variations. Now, if you see at the bottom, left bottom, this PCM container, PCM is just kept below the absorber plate also, so that it can even in the late hours, maybe after 6 or even after 7, we can attain like hot water. So there are so many number of designs even on the water heating system itself where PCM is utilized and its performance was observed to be significantly improved. Another thing that we can see here is like this is going to be a separate unit where heat energy is being stored. Okay, so this can be a separate unit as a heat storage system. And obviously, as I told, if you are using solar water heating system, your average temperature will vary from 30 to 80 degrees centigrade. Okay, this is one thing. So whatever PCM that we are selecting, we should select in such a way it is as per our application. See, there is PCMs are also being used in different ways. We can have say encapsulation. That means you use PCM inside and outside you have a shell. So when you are supplying some hot fluid or high temperature, this will not be converting to liquid and totally it will not be pouring out. But outer shell will have higher temperature, higher melting point when compared to inside PCM. And you can see here, I just kept one figure. This is a heat storage system. On the top, there is some kind of like balls, spheres are there. And if you chop it, you can see it is hollow inside. So PCM is filled inside. Now, this we say is an encapsulation. So this encapsulation of the PCM, you can broadly classify into micro encapsulation and macro encapsulation. Micro encapsulation means the size of this particular encapsulate or PCM is in terms of microns. And now people are even using nano encapsulation also. Okay, that means like our talcum powder kind, it will be there. So it is being applied to certain fluids such that it has a very good heat storage capacity. Okay, so it is being used. And towards your right, you are seeing right, it is a shell and tube heat exchanger. What is being used is at the center there is a tube where hot and cold fluids are placed, and surround to it this PCM is placed. You can see the melting process, that means without fins, with fins, and certain experiments were carried out. Okay, so obviously there are different ways by which you can use these PCMs for any like heat storage applications. If, for example, you are trying to see like list out organic PCMs, let us take, you will have thousands of PCMs that are available. So now it is our turn. Among these materials, as I told, first you will go in such a way. For example, my application is something like 55 degrees centigrade. So you draw a line from here to here and see how many you may have again encounter something like 20 PCMs. Next question comes, among these 20 PCMs, you need to go for some selection criteria. That means what PCM is like having very high latent heat. And again comes phase segregation issue is there. What is its thermal conductivity? Whether it is available, what is its cost? All the things will come next. These are also important, provided if you have more options. Okay. So in a nutshell, if you type any phase change material, you will have thousands of materials that are popping up. But first, as I told, you have to select a PCM as per your application temperature range. Next, important thing or important property is that high latent heat. Why? Because if you are going for high latent heat, its temperature will be like, sorry, its volume will be less. Okay, it becomes like more compact, and rest comes like other properties also. And if you see, even in solar thermal devices also, you may have to store heat at 250 degrees centigrade, or it might be 1500 degrees centigrade. Towards your left, whatever picture that is being shown is Fresnel lens based. It is a linear Fresnel lens by which we can have the power generation. Actually, power is being generated by using Fresnel lens, and right side what you have is central receiver system. You can say like small, like it looks small, but each mirror, whatever it is present on the right bottom picture, this is in terms of few meters square. But if you go close, it will be very big. So what is going to happen is, what are these heliostats? Helio means sun, stat means stationary. That means each mirror will track the sun and it will make sure it is being reflected to one particular receiver. So that is why this kind of system is called a central receiver system. You believe me, actually, with this, as the concentration ratio is high, we do can can melt some metals also. We can attain more than 2000 degrees centigrade. So even you might have heard about solar furnaces. So solar furnaces, the technology that we can use here is like central receiver system. Why I'm basically telling here is that your temperature is not same. For certain cases it is less than 100, for certain cases it is nearly 250, for certain cases it is around 1000 and so as per our temperature, as per our requirement, we have to select a PCM. Let us take you have central receiver system where your temperature is something like you are maintaining 500 degrees C. So definitely you cannot go for organic PCMs. You have to go for inorganic PCMs. Okay, so you can see here, this is the portion where, sorry, this heliostat field is there, and all these heliostat reflect the radiation to one central receiver system. This central receiver system, some fluid is made to pass, heat transfer fluid, and this heat transfer fluid takes the heat and it is stored in some heat storage medium. Generally, this is molten salts we generally go for, but which comes under inorganic PCMs. Generally, inorganic PCM's problem is corrosion and phase segregation. So, and whatever heat that is being stored, it is being run to a turbine, just like our Rankine cycle. And this turbine is connected to the generator and we get the power. This is like a regular Rankine cycle that we have. Our specialty will be coming how you effectively store this energy and how you effectively retrieve the heat back. So if you just see, because this is at high temperature heat storage, we can classify. So we do have certain class of materials. I just mentioned in different columns, bucket 1, 2, 3, and 4. So if you see, you do have like sodium hydroxide, sodium chloride, which is in different percentage. And if you see, its melting point is also different. And heat storage capacity is also different. So what we need to look in here is, one thing is that obviously melting point. Next comes high latent heat. And obviously comes the compactability, phase segregation, and what is its like thermal reliability, and all the things need to be seriously looked in. So that is why all this analysis becomes very much important, and especially when you are going for any application, this what I can say, characterization also becomes very important. Now, I thought it will be a good platform to mention that few examples, whatever I am giving here are very, very few. Few examples I thought like I can discuss. Let us take, if you take any photovoltaic panel, but what I could find is few electrical background people are also there. As most of you are aware of, your PV panel performance will be good if your solar radiation is high. Parallelly, other side of the coin, what we need to look in is, if the temperature is increasing, its performance will be down. It will be decreasing. For example, for every 1 degree centigrade raise in temperature, 2.2 millivolts drop will be there, because of which the overall power output will come down. So one such option is that they go for encapsulated, macro encapsulated. You are seeing some packets at the left, right? And it is not only in this way, by different encapsulation methods, it is being used. And what is observed here is, the life of the photovoltaic panel was observed to be better, and obviously its performance was also observed to be improved. There are several medical applications. So usually if you take like there are PCM based thermal pads are there, or cooling pads are there. Usually if you take our normal body temperature 36.1 to 37.2, if it is less there is a problem, if it is more there is a problem. If it is more than 37 also, we say that thing as a hyperthermia. It is heat related conditions characterized by abnormally high body temperature. So usually the internal body temperature will significantly increase. So a body temperature is more than 40 degrees C, or in general 104 Fahrenheit is defined as severe hypothermia. So what happens is, in order to restrict the rise in temperature, people use like PCM based like cooling pads. And other side, hypothermia. So a person needs a serious medical condition when the temperature drops, body temperature drops less than 35 degrees C. So then what happens is this PCM, as it is able to maintain or take or supply heat at nearly constant temperature, especially for these applications, it is going to be very promising one. And another thing is transportation of blood. Usually there is a issue called hemolysis. That means the red blood cells get ruptured or it gets distracted. And usually what happens is if this blood is being carried out and there is a vibration because of bumpy roads and so on, or if the temperature is above 30 degrees centigrade or below minus 20 degrees centigrade, the blood products are going to undergo hemolysis, which is of no use. So ideal temperature that you can maintain here is around 1 to 10 degrees centigrade. So one best option that we can go for is like going for a PCM based system. And one more important thing is the vaccine cold chain. Usually most of the vaccines, measles, yellow fever, oral polio, injected polio, and you take so many, you name it, like we do have several vaccines where it has to be stored between 2 to 8 degrees centigrade, nearly 6. So usually right from the manufacturing and the end user, you have to maintain from 2 to 8 degrees centigrade. And for this also, PCM is like a promising option. And now, especially some of you might be there from civil engineering also. Now what people are doing is people are combining in the construction. That means they are making this nano encapsulated PCM, micro encapsulated PCM. They are mixing with the cement, or they do macro encapsulation and laying in between the brick, and they are constructing using for construction. Especially in Europe, this kind of technique is being extensively followed to regulate to maintain almost like required temperatures and comfort conditions inside the room, irrespective of what extreme conditions we have at the outside. And one more thing is that thermal management of electronics. So any operating electronic component need to be operated at a particular temperature range. We say that thing as an operating temperature range. If it is beyond, or if it is beyond a particular operating temperature range, the electronic component may fail. So PCM is observed to be a very promising solution. And several applications, like one of the application is like firefighter suit. What? Because they expose it to highly extreme or high temperatures. So we do have some market. I just gave some link also at the bottom, and it actually regulates the temperature. And for refrigeration purpose also we do have, and cold car, especially certain products where this needs to be maintained low temperatures when compared to surroundings, these are considered to be a better option. And if you remember, some time back I did mention about solid PCM. This is one such kind. This is nothing but now everyone might have heard or might be working on battery thermal management system. Because usually if you see any lithium ion battery, let us take lithium iron phosphate, manganese oxide, cobalt oxide, whatever you take, it should be operated mostly between 15 to 40 degrees centigrade, or at the most 45 degrees centigrade. You need to maintain within this to have an optimum performance of the battery. And what is observed is like this PCM is observed to be a very promising option here. And left hand side, you can say solid PCM. Usually it takes the heat, but it is not converting to liquid phase. And one of the drawback what PCM can experience is its low thermal conductivity. So people are now using, researchers are now using nanoparticles, metal nanoparticles, fins, metal foam. You can see at the right side, this is a metal foam. So what they do is to improve the thermal conductivity, they totally fill the PCM in this metal foam, and they try to have an advantage of improved thermal conductivity, and the heat can be extracted or stored effectively at nearly constant temperatures. This is also one example for battery thermal management systems. Now I'll show some pictures. What do you mean by compatibility? What do you mean by phase segregation and thermal stability? See, actually this is a shell and tube heat exchanger. That means these are tubes inside where heat transfer fluid is made to pass, and outside to it there is a PCM. So you can see towards your right, it is totally getting corroded. Okay, so we did some few experiments in our lab also. So we took some different aluminum, copper, stainless steel, like different, and tried to do this corrosion test. So ASTM given standards. So what is observed is immersion corrosion test we did, and we did acceleration tests. And what surprisingly we observed is, especially for aluminum, where we consider it is because of its less weight and relatively high thermal conductivity, were observed to experience pitting corrosion. That means slowly small holes will be formed, and the PCM in liquid state or heat transfer fluid will mix, and overall performance will deteriorate. So this is one of the very important aspect where we could observe, like when we are going for a selection for any container material, in combination with PCM, this corrosion study is must. This is phase segregation. What do you mean by phase segregation? Usually, if you have a PCM, when you supply heat, it should be totally converting to liquid. And when you expose it to cold environment, it should totally convert to solid state. That is what it is expected. But certain class of inorganic PCMs, one such example, what we did in our lab is sodium acetate trihydrate. So if you observe towards your left picture, the bottom portion is like in solid, and the upper portion in the sphere, whatever like glass flask that we have taken, spherical container, on the top it is still in liquid. And what we did is we kept in a constant temperature path, and for 80 at exposed at 80 degrees centigrade for 10 hours. You can see this phase segregation. And towards your right, okay, let us assume you have a PCM which is totally converted to liquid state. Now, if you cool, you have to convert that thing into solid state. But even cooling at room temperature for 2 days, you do that phase segregation was observed. Phase segregation means two different phases were noted. So if you are observing this kind of phenomena in any of the PCM, we cannot go for a selection. But people started, like researchers worked on it, and especially there are some very attractive PCMs where it is easily available, cost is less, melting point is good, high latent heat. So they are now using nucleating agents. Nucleating agent means they add some foreign particle. We have that homogeneous nucleation and heterogeneous nucleation. And some of the PCMs were observed to even observed to get improved by this particular process. And this is thermal stability. So certain heating and cooling cycles, if you observe here, whatever curves that are shown, it is at that means when you have a new PCM which is not utilized at all, the performance is something like this. And when you go for 1000 number of cycles, its performance is coming down. For example, whatever crest or valley, that kind of thing you have here, more valley means like more latent heat. But as you continuously use for certain number of cycles, what is observed is the performance is going to get deteriorated. So especially this thermal stability is also one of the important criteria. And now, especially this characterization, that means how do we measure? This is going to be the last thing. I'll just give an outline of it. So when you are using a PCM, whether it might be for thermal energy storage or whether it might be for any application, as I have mentioned, you have several applications over here. Characterization is must. So what we need to do, we need to find its melting point, latent heat, and specific heat. These three properties you can get from different DSC. We say differential scanning calorimetry. Next, thermal conductivity. There are several equipments here. One such equipment what we used is TPS 500S, which is called thermal conductivity analyzer. Next is viscosity, because heat transport, when it is totally converting to liquid state, if you want to retrieve the heat back, viscosity should be as less as possible. So in liquid state, we need to find its viscosity, where we did with rheometer. Thermal expansion coefficient. What do you mean by thermal expansion coefficient? For example, you have in solid state PCM, and if it is now converting to liquid state, there should not be any significant increase or change in volume. So thermal expansion should be as minimum as possible. Next is density. Why density? Because you have to select a PCM whose density is high, such that system is like more compact. So for that we use picnometer. So this is one DSC. Once you take a sample, I will not go in a much more detailed manner. Okay, because already we are done with the time. So one thing is that here, whatever pointer I am showing here, this is the curve that you will be getting. So the area under this curve will be getting latent heat, and this is actually called onset temperature and endset temperature. As I told earlier, you will not be having a single value for melting point. It is usually a range. So when you are selecting a PCM, this range should be as minimum as possible. And next is, this is a rheometer experimental setup. We used rotational rheometer technique, where you have two cups which are being rotated, and by the method of simple shear flow, this viscosity is actually can be obtained. So this is a TPS 500S. We do have a sensor, and towards your left, you can find a sample holder. So the sample is placed inside this sample holder, and in between the sample holder, this sensor is placed. And this is on Goddard hot plate based, where we can find the thermal conductivities in solid state and liquid state. And this is a picnometer, where we can find the density of solid and liquid PCMs. So and in this particular process, in this particular method, so we have to use dodecane. Why? Because it does not get, is not miscible with the PCMs. Next, this is a thermal expansion coefficient. How do we define change in volume to the original volume divided by its change in temperature? So we kept in a hot bath, and initially it is in solid state, and once we expose the heat and maintain nearly constant temperature oil. So one thing I would like to add, especially this PCM has huge number of applications. It is not only about thermal energy storage. So, but the thing is, I did get several queries, especially they are using the PCM. But the problem is that PCM, instead of actually improving the performance, it was deteriorating the performance. Why? Because of improper selection. So, especially it should be done in a very careful manner as per the application and at what temperatures we are looking for. This becomes very, very important aspect. Otherwise, it is going to have a negative effect.
Sir, thank you, sir. Nice presentation, sir.
Thank you, sir.
Thank you so much
And,
for accepting our invitations, and you spent for valuable time, sir. And
pleasure,
really, many of my friends also joined, sir. After seeing my status, they asked personally for your link.
oh, thank you, sir.
My guide also
Thank you.
asked, sir.
Oh, thank you so much, sir.
They also joined, and she is working as a government institution, sir. So she also
Oh.
asked, I want to attend the session. So I personally shared the link. But madam not registered in that program.
Oh, okay, sir. Thank
Okay,
you.
sir.
Thank you so much,
Topic
sir.
is very interesting, sir, and thank you so much, sir. I will send that participant feedback to your WhatsApp, sir, or mail, sir.
Sure, sir. Thank you.
Okay,
Thank you
sir.
once again, sir,
Thank you so
for
much,
this
sir. Now I am
opportunity.
closing, sir, section.
Yes, sir. Thank you,
Thank you,
sir.
sir.